People quiet. Morning, Mr. Girijan.
Yeah, good morning, sir.
Sir, shall we start now? Let the students come in. We will start.
It's already 10.
Yeah. So, good morning. Good morning to all. I request our colleague Dr. Nagaraju to start the session. Over to Dr. Nagaraju, please.
Yeah, good morning. Thanks, madam. A warm greeting to all. I am Dr. Nagaraju Kirru, coordinator of the 4 days National E-Workshop on Modern Analytical Techniques for Material Characterization. I would like to welcome you all participants to the Thursday workshop on behalf of Geetham Deemed University, Bangalore campus and Department of the Chemistry in association with Toswin Analytical Private Limited. Okay, I welcome to today's session research person, Mr. Girijan sir also. We have a great success since last 2 days about UV spectroscopy and IR spectroscopy, and we would hope to all participants for your continued support for today's session and tomorrow's session also. Today's session is on thermal analytical techniques. Designing and fabrication of materials with good thermal characteristics is very important for multifunctional applications for nanomaterials. These thermal analysis is a group of techniques that characterize the thermal properties of the materials to measure the temperature changes, what are the chemical and physical properties of changes behind that materials. And with these techniques, we are analyzing the temperature changes. I think nowadays and right now, no single thermal analysis tool or technique works best in all the materials, but that means all the solutions. So that accurate thermal assessments require a combination of different analytical techniques, like different types of analytical, like TGA, DSE, so on. So I hope to this session presents a basic principle of thermal systems and describes some of the techniques and the tools available on the thermal characterization of some materials. Okay, I think with this brief note, I would like to hand over this session to Mr. Girijan, today research person to this workshop from Toswin Analytical Private Limited, and I would like welcome to Mr. Girijan sir. I think you should share your ideas and your knowledge about our participants based on the thermal analytical techniques. I welcome to Mr. Girijan sir. Screen is yours now. Then you can share your ideas with our participants.
Thank you, sir. Thank you.
Thank you, sir.
And a warm welcome to all the participants. Today we are on the 3rd day of this webinar series. And today we have another interesting topic to discuss, thermal analysis and different thermal analytical applications.
Sir, Girijan sir, sorry to interrupt you.
Yeah, please.
So, yesterday you have given some assignments to the
I'm going
right?
to start with that.
Okay, just to remind you.
Yeah. So before I go to my topic of discussion today, yesterday, if all the students they remember, the last slide was five very simple questions on IR spectroscopy. I will take hardly 2 to 3 minutes time. I will read out the questions and anyone can answer. I will appreciate if anyone can unmute the phone, unmute the microphone and give the answer. Number one, what is the major difference between a dispersive IR and an FTIR? These are all, yeah, I feel these are all one sentence answer we can give. Very simple questions. If you have listen to my discussion yesterday, you can answer this without any problem. What is the difference, major difference between dispersive IR and FTIR?
Mr. Girijan, the participants do not have access to the microphone.
Okay,
they can probably answer the questions in the chat box.
Okay.
Yeah, we'll let you know.
No, Dr. Vikram, they can raise their hands so that we can allow them to talk.
Right.
And Manu Dwivedi, actually, he gave answer. So what he gave is does not use a slit and less refraction loss. That is his answer.
Any other answer coming?
No, he only gave. And one more, yes.
What is the answer given by this person?
The Manu Dwivedi gave his answer as does not use slit and less reflection loss. Maybe FTIR. And one more answer came in. She is Reshmi Kundur.
Yeah.
She answered one frequency used at a time in dispersion IR. That is her answer.
Okay, she is, I think, coming very close to the answer.
Yes.
The right answer can be a dispersive IR is always a sequential measurement, whereas an FTIR is a simultaneous measurement. And one more sentence they can add: a dispersive IR uses a monochromator, whereas an FTIR uses a interferometer.
Okay.
That can be the right answer. Okay.
Yes.
I'll go to second one. How is the interference pattern generated in an FTIR? How is the interference pattern generated in an FTIR?
If anyone to answer, raise their hand so that I will allow them to talk. They can answer orally. Or otherwise, Sir Manu Dwivedi again, he gave answer by the displacement of moving mirror.
Correct. Okay. That is all what he said, no?
Yeah, by the displacement of moving mirror.
No, he is coming almost very close to the answer. I mean, more or less is true. See, we are creating an interference pattern by creating a difference in the optical path length with the movement of the moving mirror with respect to the fixed mirror. So we are creating a path length difference by moving the moving mirror with respect to the fixed mirror. And because of the difference in optical path length, the interference pattern is created in FTIR. I think he was coming very close to the answer. And the third one is a very simple question. What is the difference between a demountable cell and a fixed path length cell as far as analysis is concerned? What is the difference between a demountable cell and a fixed path length cell? If no answer is coming, I will answer it.
Yeah, it seems no, sir.
Okay. Demountable cell is used only for qualitative analysis, and fixed path length cell is only used for quantitative analysis. And one more sentence I can add: demountable cell can be opened by the user, whereas fixed path length cell should not be opened. It's only for quantitative analysis. A demountable cell is only for qualitative analysis. Next one is what type of a detector is commonly used in FTIR?
Sir, your voice is breaking. Could you please repeat that question?
What type of detector is commonly used in FTIR? What is the type of detector?
Yes, we have two answers. One answer from Kanagartha. So pyroelectric detector,
Very good. Very correct. Very correct.
Yeah, and one more answer from Manu Divedi. Pyroelectric detector.
Pyroelectric detector is very correct answer. Correct. Why? Good, good.
Great, sir.
Yeah, it's a good. It's the right answer.
Yes.
And I'm going to last question now. Why FTR quantification is little difficult as compared to quantification by UV? Why FTR quantification is a little difficult as compared to quantification by UV?
And one answer came in, sir, from Dr. N. Kanagatara.
Okay.
Different frequency bands.
Different
frequency bands, and Manu Divedi gave answer because it is a qualitative technique.
Okay. The answer can be IR also can be, even though it is used as a qualitative technique, it has got excellent capability for quantification also. But why it is a little difficult as compared to UV? In the case of UV, you have a more or less you have a single band, very broad band you are getting in UV. Whereas in the case of IR, you are getting multiple absorption bands, and you need to select a specific band for the compound without any interference for doing the quantification. That is sometimes maybe a little difficult. So that's the reason why IR quantification is a little difficult as compared to UV quantification. But we can do a lot of quantification by IR also. I think that was the last question. And with this, I think I will directly go to our topic of discussion today. And my colleague also has joined. Mr. Malleshwar Rao is there. He's a very knowledgeable person on thermal analysis. So he will be taking up the software part after once I complete my session. So I'll start sharing my screen.
Girijan, sir. Girijan, sir?
Yeah, tell me.
Yeah, one more answer came in.
Yeah.
Let me read it.
Okay.
B dash in day gave answer since crowded pattern and overlapping with closed bands. And another one is UV based on electronic transition, while IR based on vibrational transition.
Okay. What is said, the first part is coming very close because there are so many absorption bands. Sometimes so many bands are very close together, and it will be very difficult for us to find out a very selective and a very specific band for the compound because of all these multiple bands coming in. That is the reason. So he was coming very close to the answer. Very good.
And one more thing, actually, it is the IR is very sensitive to the moisture, the atmosphere, and CO2 gases.
Yes.
That also disturbs the real sample spectrum, as it is very sensitive.
But we have a lot of safety measures inside the equipment to take care of the moisture. Yesterday, Amol was telling there is a built-in dehumidifier inside. And we have a closed system. We have silica bags inside. So there are a lot of ways to protect, because the most important part to be protected in FTR is the beam splitter, because it is made of potassium bromide. And so we have to take a lot of precautions because potassium bromide is very susceptible to moisture. But we have enough adequate precautions inside the equipment itself to take care of the moisture. Okay. So, so the screen is visible to everyone?
Yes, sir. It is
okay. Today we are going to start with a different topic, thermo-analytical techniques. Very, very important analytical technique in a very vast field. And many of the industries, many of the segments, we have got plenty of applications for thermo-analytical techniques. And in general, we call it as thermal analysis. Okay, so let us start with what is the basic definition, a very simple definition of thermal analysis. Measurement of physical and chemical properties of materials as a function of time using a controlled temperature program in a specified atmosphere. Very simple definition. USP also gives a definition for thermal analysis. So measurement of physical, chemical properties of materials. That means when a sample is subjected to either heating or cooling, some changes are going to take place. The changes can be physical in nature or chemical in nature. So we are going to measure those changes, measurement of physical as well as chemical properties of materials as a function of time using a controlled temperature program, because we are going to either heat the sample or cool the sample in a very controlled fashion in a specified atmosphere. Why we are specifically telling a specified atmosphere? Because most of the time, unless anything is specifically mentioned, we always use a inert atmosphere, and most of the time it is nitrogen atmosphere. Because when the sample is heated, it should not undergo oxidation if there is a air inside or something. So we need to have a inert atmosphere, and most of the time it is nitrogen only. So unless anything is specified, we use a nitrogen blanket, nitrogen atmosphere. So measurement of physical, chemical properties of materials as a function of time using a controlled temperature program in a specified atmosphere. So that becomes the very simple definition of thermal analysis. And what is thermal analysis? We have got a material. It can be either heated or can be cooled also. Both are possible. Heating is also possible. Cooling is also possible. So when the material is subjected to either heating or cooling, a lot of changes can take place. And some are physical, some are chemical. And few of the important changes we can think of: the enthalpy can change. Enthalpy of the heat content, enthalpy of the material can change. Weight can change. That means there can be either weight loss or weight gain also. Weight can change. Dimensions can change. Viscoelastic properties can change. Sometimes the material can decompose and some gases can come out. And there are a lot of others also. Okay, for example, in the case of there is an enthalpy change, we can normally detect it by DSC. Weight change, if suppose the sample is heated, when there is going to be a change in the weight, it can be detected by, it can be measured by either a TGS system or a DTG system. And if there is a dimension change in the length, for example, dimensional change, we can use a TMA system. TMA stands for thermomechanical analyzer. We can use a TMA system. If there is a viscoelastic change that is happening in the material, we can use a DMA system, dynamic mechanical analyzer system. If the sample is undergoing decomposition and it is going to give out certain gases, and these gases can be analyzed and find out what type of a reaction has taken place in the sample, how the decomposition has taken place in the sample. And this analysis is called EG analysis, evolved gas analysis. So there are different types of information can be taken out for the sample in a thermal analysis, and there are different types of equipments available for that. Now, what is the very purpose of carrying out a thermal analysis? Number one, characterization of material. Melting point of the material can be found out. Melting point is a pointer towards the purity of a material. Everyone knows as a pure compound has got a well-defined melting point. If there is a deviation from the melting point, that is an indicator that the sample may contain an impurity. It is not a very pure compound. So melting point is a very important physical property. Crystallization temperature, glass transition temperature, especially when we talk about polymeric materials, glass transition temperature, TG, decomposition of the material, all these can be studied. Short-time evaluation of chemical reactions like evaporation, decomposition, sublimation, oxidation, reduction, even cross-linking in case of polymers. So these can be evaluated. Measurement of thermal characteristic values like melting point, purity, specific heat capacity, softening temperature, expansion coefficient. So there are a lot of information that can be taken out by carrying out a suitable thermal analysis technique. And when we talk about thermal analysis methods, there are so many different methods and certain parameters. When you are using a certain method, a certain parameter can be measured. And for measuring that parameter, we need to we need to use a certain instrument also. For example, we talk about thermogravimetry, TG. It's a very short form, TG. Thermogravimetry. What is the parameter we are going to measure is the change in the mass. And what is the equipment to find out this? We are going to use a thermobalance. We are going to use a very, very sensitive thermobalance. That's the instrument that is used. Then we are going to differential thermal analysis, DTA. And what is the parameter that we are going to measure? The difference in temperature between the sample and their reference compound. And then we use a DTA apparatus. We are going to see how the DTA works. Differential scanning calorimetry, in short, it is called DSC. It's a very, very important technique. And what we try to find out is the change in the heat content, dH by dt, enthalpy change. And we are going to use a DSC instrument. Similarly, when there is a change in the thermomechanical analysis, TMA, we are normally the parameter what we are going to find out is the deformation. That means changes in the dimensions, volume, all those, and we can use a TMA equipment. So like that, there are a lot of techniques available, and for each technique, we are going to measure a certain parameter, and for measuring that parameter, we are going to use a certain equipment also. So one of the most commonly used thermal analyzers, one is DTA, differential thermal analyzer. Second one is DSC, differential scanning calorimeter. Third one is TGA, thermogravimetric analyzer. And TMA, thermomechanical analyzer. TMA is not that very common. Even though it is a very important equipment, it's that very common. But the most common equipments are DSC as well as TG. So these are the two instruments which are very widely used in industry also, various segments of industry. So types of data that can be taken out from a thermal analysis: crystal perfection, polymorphism, especially pharmaceutical drugs, polymorphism, melting temperature, sublimation, glass transition, dehydration, evaporation, specific heat. So a lot of data can come out, and such data are useful in the characterization of materials with respect to compatibility. So when I'm talking about a formulation, it can be a polymer formulation, it can be a pharmaceutical formulation. We normally talk about compatibility. So compatibility can be studied, stability of the material can be studied, packaging and quality control. So we have got widespread applications for thermal analysis in various areas. So applications, some of the areas where you can apply thermal analysis: perfumery compounds and cosmetics, pharmaceutical industry, very major applications, organic and inorganic chemicals, catalysts, building materials, then polymers and plastics, fibers. So there is, you can see a wide area where thermal analysis can be applied, and very, very informative output can be taken out. So let us start with first DTA and DSC, then we'll go to TGA. DTA stands for differential thermal analyzer, and DSC stands for differential scanning calorimeter. So what is the principle of DTA? And we know when we are going to use DTA, we are going to measure the difference in temperature between a reference material and the sample under consideration. So differential thermal analyzer measures temperature difference between a reference and the sample as a function of time in a specified atmosphere. Again, I'm using the term specified atmosphere because unless anything is specifically mentioned, we are going to use nitrogen. Okay, so it is always a nitrogen. By default, we are going to have a nitrogen atmosphere for carrying out thermal analysis. The temperature difference between the sample and the reference we can call it as delta T. That is due to the phase transitions detected by a thermocouple. So thermocouple is the detector that is used in a DTA, a thermocouple, and it is converted to electrical signal and measured. The signal is measured in microvolt. So there is, I mean, when you talk about DSC, the output is going to be different. We talk about units. This is in terms of electrical units, microvolt. Okay, the temperature difference between the sample and the reference material. Okay, so this is how the basic things work. We have got 3 to 4 milligrams or at the most 4 to 5 milligrams. So sample is more than sufficient for a DTA experiment. Okay. So,
Sir,
yeah, please tell me.
Sir, actually, you know, some problem with your internet connectivity. You were frozen for a couple of seconds before that. Could you please start from first onwards?
I mean, right from the first.
No. This slide first.
Okay.
This slide from beginning.
Okay. So, DTA, we have a furnace. In DTA equipment, we have a furnace. And the furnace has got two sides, two positions, one for reference material and one for sample material. And we are going to keep the sample in sample pan, sample cups. And there are different materials can be used for making. Aluminum is available, platinum is available, different types of sample cups are available, sample pans are available. And the amount of sample required is also very less, hardly 3 to 4 milligrams sample. That is the quantity that is required for carrying out a DT analysis. So normally what is the reference material we use is a very, very stable compound, thermally stable compound, like for example, alumina. Alumina is a very, very stable compound. Nothing happens. It has got a very high temperature stability. And that is the standard we normally use in the case of DTA. And also DSC. Okay, now, if no standard is available, suppose in case if you don't have the reference standard with you, even then you don't have to worry. You have to keep a empty pan on the reference side. Suppose if you are using an aluminum pan, keep an empty pan on the reference side, that's all. But if you have the reference material, I mean, you can keep a small quantity of the reference material in the pan and then keep it. Otherwise, you can keep an empty pan. And the sample side, you have to mix your sample well and take about 3 to 4 milligrams or even maximum 4 to 5 milligrams of sample you can take in the sample cup and keep it on the sample side. And then if you look at this is connected to, so we have a thermocouple and we are going to heat this system at a control with, that is we have to decide what is the rate of heating that is required. You can decide what is the rate of heating. Suppose you want to heat at 5 degree per minute, 10 degree per minute, 15 degree per minute, that you need to optimize. And that means you are having a controlled heating program for the sample, the furnace you are going to heat. And then at every point of time, we are going to measure what is the difference in temperature between the sample and the reference. And if there is some change taking place, most of the time, your reference material is a very thermally stable compound. Nothing will happen to that. Even if you are heating, is a very stable compound, thermally stable compound. No changes will take place in the reference side. Whereas in the case of sample type, depending upon the nature of sample, it may undergo some change, some physical change or chemical change, but whatever is that, at that point of time, there can be a difference in temperature whenever a change is occurring. And then that temperature change is very precisely measured by the thermocouple. Okay, now this is what happens. Madam, it is okay now. Yeah, we are able to hear me very clearly.
Yes, sir. Yes, sir. It
Okay.
is perfect.
Now, look at this slide. You can see two different lines. One is a green line, one is a blue line. The green line represents the reference material and the blue line represents the sample. And we are going to start heating both reference and sample simultaneously. Normally, we start from a low temperature. Low temperature in the sense we normally starting from, say, room temperature, whatever it is. I mean, normally, if nothing is specified mentioned, we normally start from room temperature. And then we start heating. You can see both the lines are going up. The temperature is slowly rising. No changes are taking place because both the sides, the temperature are same. And then at one point of time, you can see the blue line becomes flat for some time, whereas green line is continuously increasing. Okay, so because green line represents the standard material, a thermally stable material, no change is taking place, temperature is increasing linearly. Whereas at one point of time, you can see the blue graph becomes flat for some time, and after that, again it starts rising along with the standard, along with the reference. So when the moment of time or the period of time when the graph has become flat, that means that moment some change has taken place in the sample. Some transformation has taken place in the sample. Now, for example, to understand, or for the students to understand, suppose the sample undergoes melting. And everyone knows, every student knows during melting, the temperature remains constant. That is a very basic thing we know. When we do a wet chemistry analysis also, during melting, the temperature remains constant. During boiling, the temperature remains constant. And so now the material, suppose is going to melt. Till the melting is completed, the temperature is going to remain same. And once the melting is completed, the temperature is going to rise again. And so here it is what is shown. So during that period, when the blue graph has become flat, the temperature, the sample was undergoing melting. And after the melting is completed, again the temperature is rising. So now you look at the red graph, that is the DT signal. Okay. Now you are getting a negative peak. You are getting a peak in the downward direction. That is actually the melting peak. That is the melting peak. It will precisely give you what is the melting point of the compound. Okay, so this is the information what you are going to get. That is the temperature difference between the sample and the reference material. And so some transformation has taken place, and we studied that what is the transformation. In this case, it is a melting process that has taken place. Okay. Now, whenever there is a thermal change that is taking place in the sample when it is heated, there are only two possibilities. Either there can be an endothermic transition that is taking place, or an exothermic transition that is taking place. Only these two possibilities. And the third one is decomposition. Okay, so we are considering only these two, endothermic transition or exothermic transition. Endothermic transition means a transition in which the sample is absorbing heat, and exothermic transition is one in which the sample is giving out heat. So in our system, wherever there is a endothermic transition that is taking place, we get a negative peak. And whenever there is an exothermic transition that is taking place, it gives a positive peak. Okay, so any negative peak you are getting is an indication that there is a transition that is endothermic in nature. That is, heat is being absorbed by the sample. And whenever there is a positive peak, you are going to observe. So that means the sample has undergone some change wherein the sample has given out heat. It becomes exothermic. So only these two changes are, only these two types of peaks we can observe both in DTA as well as in DSC also. Now, what is the principle of DSC? Coming to DSC. So DSC is more widely used compared to DTA. There are very few users of DTA, but there are so many users of DSC. Because in DSC, you are also going to get an additional information compared to DTA. DTA gives, of course, the temperature difference between the sample and reference material, and we get an endothermic peak or exothermic peak depending upon what type of a transition is going to take place in the sample when it is heated. All those information DTA is going to give. The same information you are going to get from DSC also. But in addition to this, DSC also is going to give one more very, very important information. That is the enthalpy change that has taken place in the sample when the sample has undergone a certain type of transformation. So differential scanning calorimeter, I have underlined DSNC, that is DSC, differential scanning calorimeter. Why we call it differential? What is the meaning of the word differential? Because it measures the difference in temperature between the reference substance and the sample as a function of time in a specified atmosphere. That is exactly what is happening in DTA also. You are measuring the temperature difference between two sides, sample side and reference side. It becomes a differential measurement. Then scanning. Why we call it as differential scanning? Scanning means measurement is carried out continuously in a programmable temperature range. We are going to program the temperature. We are going to fix a starting temperature. We are going to fix a final temperature. We are also going to fix a rate of heating of the temperature. 5 degree, 10 degree, 15 degree, even less than that, whatever rate you want. I can go at a very fast rate. I can go at a very slow rate. All those things are possible. But anyway, there is going to be a programmable temperature. And then we are going to scan when this programming is taking place. We are going to scan the sample and see what changes are taking place. So it becomes differential scanning. And the last term is calorimeter. And calorimeter, every student know it has something to do with the heat measurement. Calorimetry, when we talk about calorimetry, we are always talking about heat measurement systems. Calorimetric, the temperature difference, because in case if there is a transformation taking place in the sample, there is going to be a specific difference between the temperature of reference and the sample, that is delta T. And this temperature difference delta T is proportional to the changes in the calorimetric state of the sample. Calorimetric state means the energy in the form of heat, or in simple term, it is the heat content change. And the heat content change is represented in terms of milliwatt. So that is why I told you there is a difference in the output. In case of DSC, we are getting the signal in terms of milliwatt because it is a heat measurement system, where in the case of DTA, we are going to measure in terms of microvolt. So DSC is a very, very important analytical tool because all transitions, changes in the physical properties involve heat flow. Heat flow is always the result of a temperature difference between two objects. Two objects means we have a sample side, we have a reference side, two objects. And whenever there is a temperature difference between these two sides, there is a heat flow involved. That is why it is written heat flow is always the result of a difference in the temperature between two objects. And in differential scanning calorimetry, the difference in heat flow between a sample and an inert reference material is measured continuously at all times. A simple equation is delta Q is equal to delta T by R, where delta Q is the difference in the heat flow between the sample and the reference. Delta is the difference in the temperature, and R is the thermal resistance of the furnace material. So that's a very, very simple equation relating the temperature difference to the heat flow between the two objects. Principle of DSC also, the thermogram is going to be same as like DTA, same thing what I have shown you, but additionally we are going to get a enthalpy change that is not possible in the case of DTA, but can be completely comfortably measured in case of DSC. That's why DSC has become more popular as compared to DTA. Now, same type of curve we can expect in DSC also, either an endothermic peak or an exothermic peak. Exothermic peak, as I told you, heat evolution, and endothermic peak is heat absorption by the sample. Now, what can be measured using a DSC, differential scanning calorimeter? What all things you can do? If you have DSC, what all things you can do? What all things you can measure? Qualitative analysis, fingerprinting of minerals, I mean, when we talk about characterization of materials, fingerprinting of minerals, clays material, polymeric material. So a lot of things qualitatively we can measure. Sample purity by measuring melting points. Heat capacity can be very precisely measured. Glass transition temperature is a very, very important property, especially for a polymeric material, TG. So this is also called TG, but you can see T is capital, G is small. That is TG, that is glass transition. If I write capital T and capital G, it becomes thermogrametry. And crystallization temperature, TC, all these can be very comfortably measured, very, very precisely measured with the DSC system. Now, what is glass transition temperature? Especially for those people who are interested in polymer science, TG is a very, very important characteristic of a polymer system. And how the glass transition is indicated when you analyze a polymeric material by DSC, and if the polymer is going to exhibit a glass transition temperature, how it is going to be shown in the thermogram? It is going to be shown as a step in the baseline. There is no peak. Please don't expect any peak for a TG measurement. There is no endothermic peak. There is no exothermic peak. Okay, because there is no temperature involvement. So only a step in the thermogram. You can see the steps. So initially, the baseline was very stable, flat. At one point of time, it is slightly coming down, and again it is becoming flat. So there is a step involved. So step in the thermogram, that indicates a glass transition that is taking place in the sample. Transition from glassy and brittle state to viscous and rubbery state. Many times the polymeric material can be either it can be in a crystalline form or it can be in an amorphous form. Okay, so whenever a glass transition is also going to be reversible. Okay, and it's a transit. Initially the material was in a brittle form, in a glassy state, and when it is heated, it is changing over to a viscous and rubbery state. It becomes more flexible, it becomes viscous, it becomes rubbery, and the temperature at which this is happening, the material is getting converted from a glassy or brittle state to a viscous and rubbery state. That temperature is called the glass transition temperature. Observed in glassy solids, example polymeric materials, and TG is the glass transition temperature. So TG is very, very important, especially when you are formulating a polymeric material for a certain end use, for industrial application. Lot of properties, the final characteristics of the polymeric material will also depend to a very high extent, to a greater extent on the TG of the material. Okay, so TG is a very, very important characteristic for polymeric material. So this is what is, you can see very clearly the glass transition temperature of a material. So glass transition temperature is the temperature at which higher molecular weight materials, polymers, transform from glassy state to viscous and rubbery state. Okay, what you see, look at the thermogram very closely. Left hand side, I started heating. When we started heating, the material was in a glassy form. It was a brittle material. It was not flexible. It was brittle. And at one point of time, you can see there's a small step in the thermogram, and then the sample got converted into a rubbery state. It has become flexible. Initially, it was brittle. Now it has become flexible. It has become viscous and rubbery state. And the temperature, the midpoint of the step, is actually your glass transition temperature. It can be very precisely measured using a DSC system. Crystallization temperature, TC, sharp positive peak. Wherever there is a crystallization that is taking place in the sample, you can always expect a exothermic peak, because during crystallization, heat is given out by the sample. So it is an exothermic transition, not an endothermic one. So whenever crystallization is taking place, you can expect a positive peak. That's an exothermic peak because heat is evolved. So it's a sharp positive peak that shows a crystallization. And what is meant by when a sample undergoes crystallization, there is a transition of the material from a disordered form to ordered form. I mean, we are not going into details. I mean, students also, they know when they study about in thermodynamics and entropy and all, disordered form to ordered form. It's a transition that is taking place from a disordered state to an ordered state. Crystallization. Materials can crystallize. Observed in glassy solids, example, polymers also can crystallize. And Tc is the crystallization temperature. So depending upon the type of polymer, the crystallization temperature can be different. Okay, so this can be very precisely measured by a DSC system. We can precisely measure melting temperature Tm. But whenever melting occurs, you can always expect a endothermic peak because during the course of melting, the sample is going to absorb heat. So negative peak on thermogram. And whenever a melting is taking place, the sample is getting converted from ordered form to disordered form. Tm is the melting temperature. Melting happens to crystalline polymers and glassing happens to amorphous polymers. A pure crystalline compound can have a very precise melting point. But if it's an amorphous material, it may not be having a very well-defined melting point. Glass transition can take place. Glassing happens in the case of an amorphous polymer. Now, 3 types of DSCs are there, and we'll be only discussing about the first 2 because the third one is a topic by itself. So I'll not be covering that. Number 1 is heat, but I will just cover. One slide I will share for that, the last one. Number 1 is heat flux type DSC. Second one is power compensation type DSC. Third one is called temperature modulated DSC. It is also called MDSC, temperature modulated DSC. It's one of the latest development in the case of DSC. It has got a lot of applications and usages. And what is meant by heat flux type DSC? And different manufacturers may give different types of systems. These are all design of the equipment. Heat flux type. What is the heat flux type DSC? A sample and a reference substance are placed on a metal. So we have a common furnace here. We have a common furnace for sample as well as reference. You can see the furnace here. TR stands for reference material and TS stands for sample material. So you have a common furnace. You have 2 positions, one for the reference and one for the sample inside the furnace. And these 2 are connected to a single thermocouple. There's a single thermocouple which is going to continuously monitor the difference between the 2 sides, sample side as well as the reference side. Okay. The temperature difference of the sample and the reference material is measured, continuously monitored and measured by a thermocouple. So you have a single furnace and we have got a single detector. That's a thermocouple for measuring the temperature difference. Delta T is the temperature difference that is between TS minus TR. So that is the difference in temperature that is measured. And this is actually what happens in the case of heat flux. So what is the point to remember? It has got a single furnace and it has got connected to a single measuring system. A single thermocouple is going to measure the temperature between both the sides. Whereas power compensation is a totally different design of the equipment. In the case of power compensation, we have got 2 different furnaces. One furnace for reference material and one furnace for sample material. So furnaces are different. You have got 2 different furnaces as compared to a single furnace in the case of heat flux type. Okay, sample and reference are heated by separate individual heaters. In the case of in the case of heat flux, we have got a common heater also. It is heated common. Both the sides are heated by a single heater. There are no separate heaters. Sample side as well as reference side is heated by a single heater and a single thermocouple is going to measure the difference in temperature. Whereas in the case of power compensation, furnaces are different and they are independently heated. They are not commonly heated, they are independently heated. And then why we call it as power compensation? So why when we are heating the sample with respect to a reference material, suppose if some change is going to take place, some transition is going to take place in the sample side, there will be a difference in temperature that, you know, there will be a difference in temperature delta T. Now in heat flux type, that temperature difference is directly measured. Now in power compensation, what we do, whenever there is a difference in temperature occurs, we supply additional power either to the reference side or to the sample side and see that the temperature difference is again 0. So the amount of power supplied to keep the difference in temperature 0, that is what is measured. So we are actually compensating for the power. We are supplying power to the system so that the difference in temperature becomes 0. And that supplied power is measured. That is why it's called power compensation. Compensating for the power. And that is measured. So that is what is happening in the case of power compensation. Some other manufacturers are giving power compensation type DSC, but majority of the manufacturers are giving heat flux type DSC. Because heat flux type DSC has become more popular because of its inherent qualities. Heat flux versus power compensation. Most DSCs, what you see in the market today are of heat flux type. Generally, the major advantage is heat flux type is more sensitive and more stable. Okay, then what is the use of power compensation? I am not telling that power compensation type is bad. No, I am not telling that. But compared to these power compensation, today people prefer a heat flux system because it is sensitivity is more and it's also a very stable system. Power compensation type has certain advantage. It has a faster response time because we are using smaller furnaces, individual furnaces. So power compensation type has faster response time because of the smaller size of the furnace, higher heating rate. You can use a higher heating rate again because furnace is smaller. It can be heated very fast. So these are some of the advantages. But these advantages are not a major advantage as far as the customer is concerned because these advantages are necessary in only certain types of applications, not everywhere. Especially when you are going for a kinetic study and all, probably these advantages becomes more handy. Otherwise, in general applications, they are not having a major advantage. So that is why today heat flux has become more popular. Most of the manufacturers are offering heat flux type DSC today.
Sir, Girijan, sir, sorry to interrupt you. Just curious about that heat flux DSC. You told that a single thermocouple can measure the difference in temperature of reference and sample, right? How does it possible actually?
I think Malleshwar can elaborate. Malleshwar, can you elaborate on this?
Because I'm just curious because
yeah, Malleshwar will be the right person to answer. Malleshwar, you are there?
And one more question to you.
Yeah.
That is forward DSC. That one, how you can convert the potential applied to the sample to the heat thing? Is there any equation? Because we are measuring the potential given to the both the reference and the sample to make the difference difference 0, right? How you can convert that power to?
I think these questions, I think Malleshwar Rao will be the right person to answer. So can we take up these questions during the question?
Maybe after that, yes.
Yeah, yes, he is the more appropriate person to answer these questions. Okay. So I will give it to Malleshwar to answer these questions. Okay, he's a very
maybe after your presentation.
No problem. Yeah. I'll request Malleshwar. So you can raise the same questions again to Malleshwar.
Yes.
So he will be. I am not the right person to answer this question. He is the right person to answer.
Okay. Sure. No problem.
Then we'll go to modulated DSC. Malleshwar, are you there? Hello. So modulated DSC, can you hear me? Everybody can hear me?
Yeah.
So I'm coming. I think he has already logged in, so he should be there. I don't know whether he is unmuted. I don't know.
He's in mute, sir.
Yeah. So we are coming to modulated DSC. There is a single slide that I'm going to show. Benefits of modulated DSC: increase sensitivity for detecting weak transitions, eliminates baseline curvature and drift, increase resolution without loss of sensitivity, because we are going to have two heating rates in the case of modulated DSC as compared to a single linear heating rate in the case of a normal DSC. The ability to separate very complex thermal events and transitions into their heat capacity component and kinetic components. The ability to measure heat capacity structure changes during the reactions and under isothermal conditions. Separation of overlapping transitions and direct measurement of heat capacity. So these are a lot of advantages in the case of modulated technique, modulated DSC technique. So I am not going to discuss about modulated DSC here. And it has got a downside. The data collection is a bit slow. So that's only you can consider it as a downside of the capability of a modulated system. Now, when we compare DT and DSC, we can monitor different types of chemical reactions as well as physical changes. And some of the chemical reactions that can be, and all these chemical and physical changes can be classified into either endothermic or exothermic. So some of the examples are shown here: dehydration, decomposition, oxidation, reduction, polymerization, combustion. And you can see all, either it will fall in the category of endothermic transition or exothermic transition. And they all can be studied by DTA as well as a DSC system. Similarly, we can also monitor some of the physical changes that are taking place, like fusion, crystallization, vaporization, sublimation, then glass transition. All these can be they also can be classified into either endothermic or exothermic. So basically, you can see, so whenever there is an endothermic peak, you can expect a negative peak. Whenever there is an exothermic reaction transition, you can expect a positive. And in case of glass transition, you don't expect a peak. It is only shown by a change in the baseline. That is called a step in the baseline. Okay. Now, DT and DSC has got a lot of applications. A lot of samples are shown here. Amino acids and proteins, amorphous materials, even biological materials, then pharmaceutical materials, polymeric materials. So lot of samples and different types of information can be taken out for each type of sample using a suitable thermal technique. Now we are coming to TGA, that is thermogravimetric analyzer, another important equipment that is used in different fields. And a very simple definition of thermogravimetry is the continuous weighing of a sample by a thermobalance, a very sensitive thermobalance, as a function of temperature. And you are going to heat the sample. And when you are going to heat the sample, suppose the sample is going to lose certain weight, that is, there is a reduction in the mass. Many times it can be a minute reduction. It can be comfortably and conveniently measured with the help of a thermobalance, a very, very sensitive thermobalance. So this is a very simple definition: continuous weighing of a sample by a thermobalance as a function of temperature. Thermogravimetry applications: thermal decomposition of inorganic compounds, organic compounds, polymeric materials, corrosion of metals in various atmospheres, solid-state reactions, roasting and calcining, metallurgical applications. So a lot of applications are there for thermogravimetry also. The most important part of the equipment is the thermobalance. Very sensitive thermobalance, which can measure even a minute change in the mass of the sample when it is heated. And there are different types of balances available. The most preferred one, the most common one, the most suitable one is a top loading balance. We have got top loading where there are three different types of balances. Top loading balance is there, then horizontal balance is there, and there is one more type where the balance is hanging. So, so there are three different types of balances that can be used. So top loading balance is a very popular one. It is very popular as in the sense it is very convenient for the user to use, because when when you open the equipment for keeping the sample, the platform in the sense the balance where you are going to keep the sample, it comes to your eye level. So it is very easy for you to, very convenient for you to keep the sample pan inside the balance. For once the analysis is over, you can easily take it out also, removal also. It's very easy for the customer the user to handle this. So thermogravimetry and DTA, temperature difference, simultaneous measurement is enabled. sample bottom temperature is directly measured, and the DTG60 and DTG60 are two different models of ours, and they use a top loading balance. And we have a equipment where DTA and TG can be simultaneously done in a single experiment, and we call it the DTG equipment. You can get in a single analysis for a sample, you can get a DTA signal and what is the corresponding TG signal. Both can be available.
Participants, please wait. I think it is some internet issue. It gets in sir's place. We will contact him. Participants, announcement. He is logging in. Please bear with us another 2 minutes. Hello, Mata Prasad sir, are you there?
Yes, ma'am. I'm there.
Yeah, it seems sir has got some problem. I called him. He will log in again. By that time, do you have anything video or something to play regarding what sir explaining, demo kind of thing?
Actually, ma'am, Malleshwar sir will be doing the
Okay.
Just give me 1 second. I will
Yeah.
ask them to reconnect.
Yes, yes.
So
He's
due to
doing.
the network issue.
Yeah, network issue. Yeah. He's doing it. I called him just now. So meanwhile, if we have anything, we can proceed. Participants, thank you for your active participation, and tomorrow will be our last day. And tomorrow, if anyone wants to give feedback on the 4-day workshop, please do so. I will be asking you at around 12:30
Ma'am,
tomorrow.
Malleshwar sir, hello. Sorry, ma'am. Sorry to interrupt you.
Yeah, please, sir.
Malleshwar sir is online only. So can you
Okay.
please give the control so they will get a chance?
Yeah. What is the name he is logged in?
VM Malleshwar Rao. VM Rao.
Sir is back, it seems. M. Maleshwar Rao.
Yes.
Yeah?
So
So I will promote
yes.
him as a panelist now.
Yes.
Yes. Yeah, I did, sir. Now sir is panelist.
Malaysia,
Just yes,
Yes.
sir also there. Okay.
Yeah,
No,
sir is back. Maybe after his presentation we can.
Malaysia, good morning. Now it's okay, Dr. Lakshmi?
Yeah, sir, it is.
I'm sorry, there was an interruption in the
Yeah, it happens. It happens. No problem, sir.
Luckily, I got it back. Okay.
Yeah.
So you spoke to Malaysia. Malaysia is there, no?
Yes.
Yeah.
Okay. So we were at DTG. So what is DTG? Simultaneous TGA and DTA systems, both in two in one system. Can give you a TGA signal and a DTA signal in just single analysis. That's a major advantage. So you are investing in only one equipment, but you can carry out two different analyses on a single sample at a time. So one example also that is shown there. So when you're having an analysis, you are getting two different types of signals. The blue graph, what you see is the DTA signal, and the red one, what you see is the TG signal. So that shows, so whenever there is a weight reduction, you can get a corresponding DTA signal also from this equipment. So what is DTG? Thermal properties such as transition temperature, melting point, reaction temperature, all can be measured. At the same time, weight changes which occur during some of these thermal changes can also be measured simultaneously. Hence, from a single analysis, one is able to determine whether the thermal changes are attributed to chemical changes such as adsorption and decomposition or physical changes such as fusion. That the DTG can shorten the analysis time, and only a very small quantity of a precious sample is required for the analysis. Of course, when you talk about the sample quantity, the sample quantity will be slightly more than what is required for a normal DSC analysis, because many times sample may undergo weight changes, so that we should be able to measure it properly. So normally sample quantity is slightly more than what is required for a normal DSC system. And when we go for a DTG, TG and DTA signals are going to be available to you simultaneously. So when you analyze a sample in a DTG, you can see the slide. There is a TG signal and there's a DTA signal. And the shapes of the signals also can be different depending upon what type of a change is taking place in the sample. For example, dehydration. The sample is losing water, dehydration. So in the case of TG, there is a weight reduction because water is getting removed. There is a weight reduction. So you can expect a change in the baseline. TG signal is always a step in the baseline. Normally, you know what is in your glass transition also, you find a step in the baseline. So similarly here, in the case of TG, you get a step in the baseline. Either it can be a downward step or it can be an upward step. But whenever there is a reduction in the weight, the step is always in the downward direction. Initially, the baseline is flat. It comes down and then again becomes flat. So that's a step that indicates the sample is losing weight. Dehydration, losing weight. What is the corresponding DTA signal? And dehydration is always a endothermic process. So you will get a negative peak for DTA. And now you consider oxidation. Oxidation, your weight is going to increase because oxygen is getting added to the sample. There is a weight gain. Instead of weight loss, there is a weight gain. Now you can see the corresponding TG signal is exactly reverse of what you have seen for dehydration. There is an upward shift. Initially, the baseline was flat, then it shifted upwards, again it becomes flat. So there's an upward shift. So either it can be a downward shift or an upward shift. So or in the case of oxidation, you're getting an upward shift in the baseline, and the corresponding DTA signal is a positive P, because oxidation is always a exothermic reaction, and you are getting a positive P for the DTA. So correspondingly, you can see some of the changes that are noted down. For example, glass transition. In the case of glass transition, TG will give a flat baseline. There is no change because there is no weight loss, no weight gain. So your signal is flat. At the same time, look at the DTA signal. There is a step. Step in the DTA indicates glass transition. But for TG, it's a flat baseline. So various types of signals can be observed for various types of transitions that are going to take place when you analyze a sample by DTG. And factors affecting T analysis. Sample itself is a main factor. Mass of the sample, that is how much sample quantity you take, what type of a pan you are going to use, what is the heating rate you are going to employ, and what is the atmosphere you are going to use. But these are all factors that will have an influence on the thermal analysis. Number one is sample. Sample purity is very important. Trace amounts of impurities can catalyze decomposition or cause different types of reaction sequences in the sample. Chemical composition, whether the sample is diluted with an inert reference material. And if you are going to dilute the sample, the thermal conductivity of the sample can change. And if any pre-treatment is given on the sample, so that also can change some of the thermal characteristics of the sample. So information about the sample is very critical before you take up a thermal analysis. Second one is the amount of sample you are going to take, sample mass. Size of the sample, how much sample quantity, packing, and what is the density of the sample. These are all important parameters. Crystalline samples may behave differently from powder samples, especially when surface reactions are involved. The sample amount is too little. If you take extremely small quantity of sample, your signal intensity will be very small. At the same time, if you take too much of sample quantity, the resolution also will be lost. So you have to optimize the sample quantity to get a good intensity as well as a good resolution. So you need to optimize. So many things you have to optimize yourself when you actually do the analysis. Sample pan is very important. There are different types of pans available. So you should choose the right type of pan for the right type of analysis. Sample pan should be chosen based on whether it reacts with the sample, whether the pan can catalyze some reactions. Geometric shape of the sample, because for powder sample, the pan is different. The liquid sample, the pan is different. So geometric shape of the pan is also very important. Depends on what is the type of sample you are going to use and you are going to analyze. Heat conductivity of the sample pan. Platinum has got a much better heat conductivity than alumina. So that is another factor to be considered. Then heating rate is very, very critical, because when you talk about heating rate, higher heating rate has higher thermal lag, allows sample to melt sometimes before even decomposition. And what we normally advise the users is start with a low heating rate. If you use a high heating rate, you can normally finish off the experiment in a much smaller amount of smaller period of time. But then many times, if you are going to use a higher heating rate, sometimes the resolution can be affected. It's like normal in the case of UV also. You have a fast scanning speed and a very low scanning speed. If you use a low scanning speed in UV, your resolution will be much better compared to fast scanning speed. Same way, here also, a lower heating temperature, lower heating rate, if you employ, your resolution will be always improved. So you need to optimize the heating rate also. Atmosphere is very important, but nothing otherwise mentioned. Always use a nitrogen atmosphere. That's an inert atmosphere. or there is a possibility to use a reactive atmosphere for certain types of applications where we can introduce even oxygen or any reactive gas, but they are all specifically designed for a certain types of applications. If nothing is mentioned, our atmosphere is always nitrogen. Okay, different gases have different thermal conductivity. For example, helium thermal conductivity is 5 times more than that of nitrogen. And even the atmosphere, what we are going to use when you are going to heat, what type of atmosphere you are going to use, that also will influence some of the reactions. For example, calcium carbonate. Calcium carbonate can decompose into calcium oxide and carbon dioxide, CaCO3, CaO plus CO2. Now, if you are going to use air atmosphere, this decomposition can take place somewhere around 700 or slightly below 700 degrees centigrade. But in carbon dioxide atmosphere, the decomposition occurs around 900 degrees centigrade. You know, Le Chatelier's principle. So the atmosphere also has got an influence on the decomposition nature of the sample. When we talk about some of the applications, we will touch upon some of the important applications, not only in pharmaceutical industry, but also we'll cover some of the food applications as well as polymer applications. In pharmaceutical industry, characterization, melting point, heat of fusion, specific heat capacity, water crystallization, then purity can be found out, polymorphism study can be found out, taken up. Polymorphism study is very, very important in API manufacturing. Basic bulk drugs, once upon a time we called as bulk drugs API, active pharmaceutical ingredients. Lot of drug samples exhibit polymorphism. So we'll see some examples. Then screening test for compatibility, especially when you are going to formulate a drug, especially in pharmaceutical formulations, along with the API, we are going to have a lot of excipients and how they are going to be compatible as a formulation. So that can be studied, and stability tests can be carried out. So these are some of the important applications people normally do in pharmaceutical industry. Heat characterization, melting point, heat of fusion, specific heat, all these can be found out. Melting point generally measured by normal classical method is you go for a melting apparatus. It's time consuming, and you may not be sometimes able to very precisely point out the melting point, whereas a DSC method is much faster, sample size is smaller, and you are getting a very precise measurement of the temperature of melting. And water of crystallization you can find out. See, this is melting and heat of fusion of aspirin. Salicylic acid acetate is an analgesic and antipyretic compound, anti-inflammatory, anti-rheumatic, and you can find out the precise melting of aspirin. It has got a melting temperature of 135, 136 degrees centigrade. And during the course of melting, what was the heat content change that has taken place? Minus 177.78 joules per gram. This is an additional information. The heat content, the enthalpy change, what you are getting in DSE, is an additional information over a DT experiment. So you can get at the same time, you are also getting the melting temperature. Purity study, purity is very, very important for characterizing a material and especially in pharmaceutical drugs. And we can use an HPLC for finding out the purity, but everyone knows HPLC is going to take time. There's a column involved, preparation of your mobile phase, stabilization time. All those things are to be taken into consideration. So it is going to be time consuming. And moreover, you are going to use a lot of solvents also. The consumption of solvents, reagents, all those are there. Whereas in the case of DSE, we don't require all this, no solvents, nothing. The very only thing you need to have a separate software for this. I think Malleshwar can elaborate more during his session. We have got a optional purity software. You have to take that optional software, and then it will tell you what is the molar purity of the material. Very precisely it can be measured. For example, benzoic acid. We use this partial purity software, and it has found to be 99.951% pure. Very fast analysis. No solvents are required. The only requirement is your DSC along with the optional software you have to take. polymorphism study is very, very important in pharmaceutical industry. And I hope all the students know what is meant by polymorphism. When a drug is manufactured, all the drugs are manufactured by chemical reactions. So when a drug is manufactured, it can remain in multiple, sometimes there is a possibility that the drug is remaining in multiple crystal forms. Out of this, only one crystal form is biologically active. All other forms may be biologically inactive, and they are called polymorphs. And if a when a drug is consumed by a patient, and that is I mean ultimately what is required is the patient should be cured of the problem by consumption of this drug. But if the inactive form is going inside, the patient will have absolutely no cure because it is a totally inactive material that is going inside. What is required is the biologically active material should go inside. So if the biologically inactive material, the crystal forms are formed, then it is a waste of the preparation. So the polymorphism formation can be because of so many factors. Many times it can be because of manufacturing conditions, use of certain solvents, use of certain catalysts. Many times the temperature, lot of parameters are to be seen into that. And depending upon the polymorphism formation, the manufacturing process is to be modified and see that the polymer formation is brought down to bare minimum or practically nil. So polymorphism is nothing but existence in more than one crystalline species of the drug. One form is usually thermodynamically more stable, biologically active, whereas others are not. So different crystal forms have different physical properties, such as density, solubility, dissolving rate, melting points, and the physiological activity, but the chemical properties are same. Physical properties are different. And based on that, and normally polymorphism, the best method, the best technique to study polymorphism is X-ray diffraction. The X-ray diffraction, of course, you need to have a very thorough understanding of X-ray diffraction to interpret the result. So if X-ray diffraction is supposed to be the number one method, you can use an FTR in case FTR is connected to a microscope. Yesterday we saw that when polymorphism can be studied. I mean, we have done a lot of experiments on that. Polymorphism by FTR microscope. But then DSC is going to be the simplest method to find out polymorphism because it is making advantage of the difference in some of the physical properties like melting temperatures between the active form and the inactive form. So that is why DSC has become a very popular method. DSC can be used to study stability of different forms of crystals at various melting conditions, heating conditions. No pre-treatment is needed and very, very short measuring time. So this is an example, it's a sulfa-thiazole, it's a sulfur drug, and the main drug is melting around 202 degrees centigrade. And it has got certain polymorphs also. One is a major polymorph is somewhere around 167.8 degrees centigrade. So we can differentiate the polymorph from the main drug because the melting points are different. And it can be easily measured using a DSC, and it takes a very less amount of time to complete this. So polymorphism study is a major analytical application in pharmaceutical industry using DSC. Screening test for compatibility, especially when a pharmaceutical formulation, a lot of excipients and active APIs, they are mixed together to form a formulation. What is the compatibility between the API and excipients is a major thing to be investigated. Otherwise, the formulation will not be stable. It will not be compatible. The normal storage test needs several months, and sometimes it can go to a couple of years also. But DSC can be used as an initial screening test. No interaction if theoretical and experimental thermal analysis features are the same between the original pure components and the mixture. Suppose I am going to mix, you will see an example. Suppose I am going to mix two different compounds A and B. I know what is the thermogram of pure A, what is the thermogram of pure B. And after mixing A and B, if there is going to be any major change in the thermogram, that means the compounds are not compatible. Otherwise, it has to reproduce the original thermograms. So if there is no physicochemical incompatibility, you will be able to see that from a DSC result. Okay. However, result must be interpreted carefully. See, for example, we are going to mix benzoic acid and magnesium oxide. Magnesium oxide, if I take only pure magnesium oxide, you can see the thermogram. It is a very stable inorganic oxide. You will get a baseline, stable baseline you are going to get. And if I take pure benzoic acid, it has got a well-defined melting point, 123 degrees centigrade. You can get a very clean thermogram of only benzoic acid. Now, if I am going to mix benzoic acid and magnesium oxide in a certain proportion, we can see the thermogram is totally changed. It has got a very irregular shape. So that means that particular combination of benzoic acid and magnesium oxide is not compatible. So compared to DSC curve, that measured mixture between magnesium oxide and benzoic acid, and each single DSC curve, we can see big difference in mixing. After mixing, there is a big difference in the thermogram. So in mixture, melting point of benzoic acid has totally disappeared, suggested that the change it is a incompatible combination. So that is why we can study compatibility using another example is compatibility of trimethoprim. It is an antibacterial drug, and polyvinyl pyrrolidone is a cross-linking material. And so when you are going to mix these two, you can take only if you consider only polyvinyl pyrrolidone, and that is what you see at the top. That's a green curve. It has got a very specific thermogram. And if you take TMP, it has got a very specific thermogram. And we are going to mix it 75% of PVP and 25% of TMP. And you can see the thermograms are reproduced. The combination is okay, the combination is compatible. Suppose if you grind this mixture, 25%, 75%, 25% mixture, if you are going to grind, you can see the last thermogram, it is totally changed because during the grinding process, some incompatibility has taken place. So that means you have to modify maybe the grinding temperature, the time or whatever way you are going to grind it. Sometimes you have to, or it's only physical mixing is required or grinding is required. If it is grinding is required, how much time should grind? What is the force with which it should be ground? All these things we can optimize by looking at the thermograms. So compatibility studies are very, very important, especially in pharmaceutical industry. And there is something called photovisual DSC. That means you can actually see what is actually happening inside the furnace by going. It is an attachment, optional attachment, photovisual DSC. We have even a CCD camera. We can actually see the melting process. What is happening to temperature is actually attached. This accessory is attached to the DSC, and what you see on the right hand side, what you see is the photovisual DSC. Okay. Now this is a margarine. It's a food sample, and what is the change that is taking place at different temperatures? You can physically you can see it for yourself if you have photovisual DSC type. So when it is start melting, during the course of melting, completion of melting, the changes are going to take place. So you can visually see all those changes. Okay, now measurement of sulfathiazole again by photovisual DSC. So these are some of the applications when you go for a photovisual system. Heat denaturation of proteins by DSC. The protein structure plays a very, very important role in its function. The protein structure and its function are influenced by many factors, such as solvent. Temperature is a major function. Depending upon that, if you are heating the material, and changes are going to take place. So temperature is a major function. pH of the solution is a major function. So one common method for analyzing protein stability is to utilize a differential scanning calorimeter. Okay. When the higher order structure of a protein is irreversibly changed, it results in loss of activity due to degeneration. And this is referred to as the thermal denaturation of protein. And the result is an endothermic peak in DSE. This is an example of a lysozyme denaturation at different temperatures. What is the effect happening at different pH values? One is pH 9.1, pH 7.05, pH 4.2. So pH has got a very pronounced effect on the behavior as well as the temperature also on the denaturation of the proteins, which can be easily studied by a DSC system. Then application of DTA, coming to some of the inorganic minerals. It's a mixture of different types of inorganic materials like kaolinite and all. So you can see what changes are taking place in the sample when it is heated from a lower temperature to a high temperature like 1000 degrees. So this is a inorganic application. DTA occur by polymer mixture. Different polymers are mixed. Many times we can even use even DTA or even a DSE for compatibility of a polymeric mixture also. Okay, so different types of polymers are mixed together, and wow, the thermogram is looking alike. It's a polymer mixture. And interpretation of DT occur, and one example is shown. I think I will show you that example separately later. DT occur by polymer. Glass transition can take place. If at all the polymer is going to exhibit glass transition, crystallization can take place, melting can take place, oxidation can take place, finally even decomposition can take place. So depending upon the type of transition that is going to occur in the sample, you get multiple peaks also in the system. Some are exothermic and some are endothermic also. Measurement of crystallinity of a polymeric material. Crystallinity of a polymeric material can be found out by DTA using the equation, mathematical equation, X is equal to, where X is the percentage crystallinity of the compound, delta H minus delta HA divided by delta HC. And what are these terms? X is the crystallinity of the polymeric material. Delta H is the total energy absorbed by the sample per gram. Delta HA is the amount of energy absorbed by 1 gram of a totally amorphous material. And delta HC is the heat of fusion of 1 gram of a perfectly crystalline material. So you should have a perfectly 100% crystalline standard material also for this measurement of crystallinity. Okay, this can be carried out by DTA. Measurement of a polymer blend by DSE. We are going to mix two different polymers, and we are going to see the compatibility of the system. Here we are mixing polypropylene and LDP, low density polyethylene. Okay, LDP, you have got a separate thermogram at the top, that's a red colored curve. And PP, that is polypropylene, you have got a separate thermogram, that is the middle one. And the last one, blue colored one, is the combination of LDPE and polypropylene. So if the system is compatible, you can definitely see as two separate same reproducing the original ones. So you can see, for example, LDPE was initially 115 degrees centigrade was the melting peak. Now in the blend also, it is almost 114.9. And for polypropylene, as it is 177 degree, and the mixture also, it is almost 176 degree. That means it is a stable formulation. The compatibility is good. And many times the compatibility of the polymeric system by DSE also can be measured by observing the TG. Okay, because if the if the two polymers, then you can, many times you can get a single glass transition temperature for the system. And if they are not compatible, many times it can give different values for the TG also. Heat influence of heat treatment on polyethylene terephthalate, PET bottles, polyethylene terephthalate. A sample of a PET bottle was measured by DSE. With the original sample, a melting peak was observed at 254.8 degrees. That is, we have used a DSE in the normal course, having a certain rate of heating, heated the sample, and we observed a melting period 254 degrees centigrade. It shows that the structure before melting was crystalline. Because it's a polymeric material, so it is melting. So initially, so it was a crystalline material. Now, after this, after the complete melting of the material, it was rapidly cooled. Quenching, rapid cooling was carried out, and again the material was reheated. And then during the course of reheating, a glass transition temperature was observed at 77.6 degrees centigrade, which shows that polyethylene terephthalate becomes non-crystalline when it is cooled rapidly. So you actually, what you're studying is the changes that are taking place when a sample is heated and rapidly cooled. And exothermic peak is observed at 136.8 degree, which shows that non-crystalline PET changes to crystalline form at this temperature. So all those information you are going to get. So the original PET bottle, you can see there's a single 254.84 degrees centigrade melting heat. After rapid cooling and reheating, you are able to observe a glass transition at 77.6, a crystallization at 136 degrees centigrade, and a melting again at 254 degrees centigrade. So this is a PET bottle first and second heating, and second heating after rapid cooling. After the first stage of heating, rapid cooling, and second reheating. So changes have taken place in the material. And this is the DSC system, what we are offering, our latest DSC system, DSC 60 plus. It can come in two different forms, DSC 60 plus and DSC 60 plus A. A means auto sampler, where you can keep 24 samples at a time, unattended operation, or everything will be automatic. So you can keep all the samples, then you can go. Otherwise, if you don't have so many number of samples, we have got a single sample system also, DSC 60 plus, where you have to analyze one by one yourself. Otherwise, you can go for an auto sampler option. It has got capability to analyze 24 samples at a time. Then what are the DSC application field and temperature range? So many different types of areas we can use: chemicals, rubber materials, that is coming under polymeric materials, electronics, machinery and automotive systems, food samples, pharma, cosmetics. Entire range can be covered by this DSC 60 plus. It has got a temperature range from minus 140 degrees centigrade. It can go to 600 degrees centigrade. That's the capability of the system. What is shown for this system? This can work from minus 140 degrees centigrade, cryogenic operation, and maximum it can go to 600 degrees centigrade. And if you want to have sub-zero temperature operation, there are two accessories available. Either you can have a connect a system to a liquid nitrogen tank, and automatically liquid nitrogen will be filled in a beaver flask for sub-zero operations, and thereby you can go to minus 140 degrees. But if you don't want to go to that low temperature, you need to go only up to minus 50, not below minus 50. Then we have got a different attachment, which is basically working on a Peltier system. So there are two different options. And the third one, if you don't want to go for any of these options, the only thing you have to manually pour liquid nitrogen yourself. You have to take a big stainless steel cup and you have to pour yourself manually. You have to pour the liquid nitrogen into the flask. That is also another option if you don't want to go for this type of accessories. Okay, and this is the DTG what I've shown. DTG can work from DTG. There are again DTG. There are two types: DTG 60 and DTG 60F. 60 means it can go to 1100 degrees centigrade, room temperature to 1100 degrees centigrade. And H means it is high temperature, it can go to 1500 degrees centigrade. Starting from room temperature, and it can go to either 1100 or 1500 degrees centigrade. And DTG also, you can get with an auto sampler or without auto sampler as per the requirement of the user. Okay. Balance requirement for DTG, temperature coefficient of the balance should be very low. High sensitivity and very high accuracy is required. hardly affected by buoyancy or convection in the furnace, excellent vibration resistance, and the user should be very comfortable with the balance, keeping the sample, taking on the sample from the balance should be very careful. And but top loading balance is very convenient for the people, for the user, because it comes up and then you can conveniently take out the sample and keep the sample. Only thing, you should have a very steady hand, because you are using very small sample cups and no spillage should take place. And if there is suppose your hand is going to shake, suppose the sample cup is going to fall down, then you cannot do anything. You have to call the service person. He has to come and dismantle. And please mind, the balance is a very, very delicate part of the equipment. It's very sensitive, very delicate. So you have to be extra careful with the TG system. And this is the type of top loading balance we are using. We are using this type of balance in our DTG60 and DTG60A. So you can see the sample cup is almost at your eye level. So it's very convenient. Top loading type of balance, sample and reference pans are located at the end of the balance beam. This minimizes the heat transfer from furnace section to the balance unit and very, very, very easy sample handling as far as the user is concerned. And gas supply system, there are 3 different gases that can be connected to the equipment. One is nitrogen purge gas, because we need a inert atmosphere. So we are going to use nitrogen. Reactive gases, in case if you want to study a certain sample under certain reactive conditions, reactive atmosphere, then we can do that. So there is a provision for the second gas with oxygen can be supplied if oxygen is required. Okay. And then many times after using couple of samples, you need to clean the furnace. So cleaning gas is also, normally air is used for cleaning the gas. So 3 gases can be simultaneously connected to the equipment, and then as per your requirement, you can use the gas, and this also can be changed to the gas also can be changed to software. Inbuilt automatic fan is there, because especially in the case of DTG, you are going to a very high temperature. Many times you may go to the temperatures like 800 degree or 900 degree or 1000 degree. And then once the analysis is over, you have to cool the equipment for the second sample. Cooling from 1000 degree to your lab temperature, maybe 30 degrees is going to take a long time. It's natural cooling. So there is a inbuilt automatic fan, and then it takes down the temperature very fast, and hardly in 30 minutes time, from 1000 degree, it will come back to 30 degrees centigrade. So that means basically for reducing the time of cooling, there is a inbuilt automatic fan in the system. Okay. And if you want only TG, you don't want to purchase a DTG. Of course, DTG cost will be more. Some customers may say, we don't want DTG because of the cost. We want only TG. We are interested only in weight loss or whatever changes in the weight. You can go for a system TGA50 or TGA51. But this will give only TG signal, no DTA signal will come. And TG50 and TGA51 difference is the amount of sample that can be taken. In TGA51, you can take a slightly more amount of sample quantity compared to TG50. And the rest of the conditions and temperature ranges are all same for these. And this is a decomposition of calcium oxalate monohydrate. I showed you one graph, one slide sometime back. Then I told you, I'll show you. See, overall reaction, calcium oxide monohydrate CaC2O4 H2O. And if you are going to heat in a TG system, what is the ultimate reaction that is taking place, final reaction? It will give you calcium oxide plus water plus CO plus CO2. And it happens in 3 different stages, 3 different steps. Number 1 step is CaC2O4H2O, calcium oxalate monohydrate. The water is going out. It becomes anhydrous calcium oxalate, CaC2O4 plus H2O. There is a proportional weight reduction because of the removal of water. And second stage, you are going to heat it further. CaC2O4 will decompose into CaCO3 and carbon monoxide. So there is going to be further weight reduction. And you are going to continue heating. CaCO3 will decompose to give final CaO plus CO2. there is a third weight reduction. So even in this particular compound, calcium oxide, because calcium oxalate monohydrate, if you are going to carry out a TG analysis, your thermogram will look like this. There will be three stages where the weight is getting reduced. One is removal of water, second one is removal of carbon monoxide, and third one is removal of carbon dioxide. And finally, the compound is getting converted to calcium oxide, which is quite stable. No further change of weight reduction will happen. So multi-stage reduction in the weight depending upon what type of a sample. This is again a food application. Analysis of aspartame is an artificial sweetening agent by DTG. We can precisely say what is the weight loss and what temperature is taking place. The first weight loss was around 47 degrees centigrade. There are three different weight losses. The first weight loss was around 47 degrees. You can see a very slight weight loss there. And it was because of removal, evaporation of free water in the sample. Very, very slight quantity, hardly around 1.08% weight loss. And the second weight loss was happening around 100 degrees centigrade. And because of the detachment of crystalline water. And finally, the decomposition is taking place. And that is somewhere around 180 degrees centigrade, where most of the final weight loss has taken place. So this is a typical food application. And degradation of cooking oil. So when you are actually using cooking oil at home also for cooking, and the oil is getting heated. Okay, oil is getting heated means it is undergoing oxidation also. The color of the oil can change. The taste of the oil can change. So properties of cooking oils such as taste, smell, color, all these are going to change with long-term storage or heating. Ultimately, what is happening? The material, the cooking oil is getting oxidized. It is undergoing oxidation. The main cause of all these changes in the color, changes in the smell, changes in the taste, these are all mainly because of oxidation. And TG can measure the change in the mass due to oxidation. When oxidation is taking place, there is going to be a gain in the weight. Okay. Now, how fast the material can undergo oxidation will depend upon what is the way it is manufactured by the manufacturer, whether they are adding some antioxidants in the material to prevent oxidation of the oil when it is getting heated. So it all depends upon the formulation of the material, the food material, whether it can withstand the temperature for a substantial period of time. So it all depends upon the composition. The results of TG can be used to determine the storage conditions, estimate shelf life, and evaluate the antioxidants that are added to the oil to prevent the oxidation. This is degradation of a cooking oil. Sesame oil was heated in oxygen. Absorption of oxygen began at around 152.4 degrees. The sample started undergoing oxidation. And there was a very specific increase in weight of approximately 0.31%. So you can precisely find out at what temperature it is undergoing oxidation, starts oxidation. And that also again depends upon the formulation of the material. Water content in a PET film by TG, decomposition of nylon 6 by DTG. Here we have utilized a DTG. So we got a TG curve also, we got a DTA curve also. This nylon 6 is a typical polymeric application. And I think this will be the last application I am going to show you, that is oxygen induction time of polyethylene. OIT is very popularly known as OIT application, oxygen induction time. When especially polyethylene is used for covering electrical wires and cables and cable industry and all. I mean, polyethylene is used extensively for covering the electrical cables and wires. And then they are going to, when they are under usage, the cable is getting heated up because the temperature is going to increase. Over a period of time, it absorbs atmospheric oxygen and deteriorates gradually. Antioxidants are added in PE formulation to prevent this oxidation. And this effect can be investigated by measuring the OIT by DSE. Oxygen induction time of polyethylene can be measured by DSE, and that will show the efficacy of the antioxidants that are added, or how the polymer is formulated, and what is the effect of those antioxidants, how well it can withstand the atmospheric oxidation. So all this information can be taken out by an OIT experiment using a DSE system. A sample is heated in nitrogen atmosphere to a specified temperature, and after reaching the set temperature, the atmospheric gas is changed over from nitrogen to oxygen. That means we are introducing a reactive gas now. The time from introducing oxygen to the beginning of the exothermic peak due to oxygen absorption is measured as the OIT. The moment you introduce oxygen, you start counting from there. And the time taken from the introduction of oxygen to the appearance of a exothermic peak because of oxidation, that is the time measured as oxygen induction time. This can be different for different types of formulations, and also shows the efficiency of the antioxidants that are added in the material. Okay. So this also depends on the initial temperature. Okay, this is also this time can change, the OIT can change depending on the temperature at which the change has taken place. Change means from nitrogen to oxygen changeover. It has taken place at what temperature? That temperature also has got an effect on the time, oxygen induction time. So this is a polyethylene OIT experiment, oxygen induction time of T. We have heated the material to around 190 degrees centigrade, and around 190 degrees centigrade. So we have changed over the when starting the changeover from nitrogen to oxygen. You can see that then the total time taken from after changing over from nitrogen to oxygen, it has taken around 78.58 minutes, approximately 78 minutes, 79 minutes for the appearance of a exothermic curve. So that means the material was quite stable for a long period of time, even after the introduction of oxygen. It has taken a long time, more than an hour, 78, 79 minutes it has taken for the oxidation to start. That is why the appearance of your exothermic peak is beginning at 78 minutes, after 78 minutes of introduction of oxygen. OIT, so this oxygen was introduced when the sample was at 190 degrees centigrade. Initially, we heated the sample to 190 degrees centigrade. Then we introduced oxygen, and then we started the time from there, counted the time from there, and it has taken 79 minutes for the oxidation to take place. And suppose if we introduce oxygen at a higher temperature, instead of 190 degrees centigrade, we are going to change over at 200 degrees centigrade. And then it has got a very, very drastic effect on the OIT. Now the OIT has come down to 20.46 minutes. So the temperature at which the changeover is taking place from an inert atmosphere to a reactive atmosphere is also very, very important, because that also can influence the final OIT of the material. And a quantification of carbon black in SBR, a sample of styrene butadiene rubber is heated in nitrogen atmosphere in DTG to about 600 degrees centigrade. At this temperature, the weight loss by thermal decomposition of SBR will be observed by TG. So TG can find out what is the weight loss when the sample was heated to 600 degrees centigrade. After the decomposition of SBR, the atmosphere is changed over from nitrogen to air. Air means it contains oxygen also. In air atmosphere, carbon black will get oxidized to carbon dioxide, and the corresponding weight loss can be observed and can be measured by TG. So after the changeover from one atmosphere to another atmosphere, and when there is an oxidation taking place, carbon black is getting converted to carbon dioxide because of oxidation, and there is a proportional weight change that can be measured by the TG signal. And in DTA, the endothermic peak by decomposition of SBr and the exothermic peak by oxidation of carbon black can also be observed. So that's the plus point of going for a DTG analysis. TG DTA curve of SBr, styrene butadiene rubber. So you can see all the transitions in this, the weight loss and the oxidation that is taking place. So there is a proportional weight loss in the material. All this can be studied in a single experiment when you go for a DTG. I think that was my last slide. And as yesterday, I am going to give 5 simple questions to students, and you can note down this. And then I will end my session. I will hand it over to my colleague Maleshwar Rao. So I am just giving 1 minute for the students to note down the questions. Very like yesterday and day for yesterday. These are very, very simple 5 questions you can answer. What type of information can be available from thermal analysis of a compound? Name a technique for the measurement of dimensional changes in a sample. What additional information you can get from a DSC experiment compared to DTA? What type of a reference material you will use in a DSC measurement? And if you want to find out the moisture content in a sample, which TA technique you will use? Very, very simple questions. You can answer in hardly about a minute's time, all this. So tomorrow morning, tomorrow is the last day of our session. I'll be talking about gas chromatography tomorrow. And we need to, I have got a request to the students, please be on time tomorrow because we need to complete everything by 12:30 because after 12:30 there is a winding up session. So that is going to take some time so that everything can be completed by 1 o'clock. So all the students, my humble request is please let us start the session exactly at 10 o'clock. Don't be late because then otherwise I will not be able to complete. I'll have to skip so many things. So I expect all of you to be there by 9:50. Today also I saw even at 10 o'clock there were hardly 40, 50 or slightly more than that participants. I feel that should not be the case. Most of the participants, I request you to be on time. Coming at 9:50 and joining when I am here, I am joining the session at 9:30. I am getting ready by 9 o'clock. I am sitting in front of my PC at 9:30. I hope all my student friends also can. We are not calling you at a very early morning time. 9:50 is a very convenient time. So let us start the session on time. Tomorrow is also a very, very interesting topic for discussion. It's a very lengthy topic, but I will try to complete by on time tomorrow. So provided you also cooperate with me, let us come start the session on time and let us end the session also on time. With this, I am handing over. Thank you once again for being with me, and I will hand over the session to my colleague. Maleshwar is a very, very experienced, very experienced person, very knowledgeable person in the field of thermal analysis. And you can ask whatever questions, and Maleshwar will be able to answer those queries. Over to Maleshwar.
Yeah, thank you, Girijan.
I will stop sharing my screen.
Sir Maleshwar, sir, you there?
Very good afternoon, very good morning and good afternoon. And I'm sharing my screen. By the way.
Yeah, please, sir.
Is it visible?
Yes, sir, it is clear.
Very good afternoon to all, and thank you, Girijan-san. And I'm Malleshwar Rao from Toshwin Analytical. I'm actually covering after sales support, and I'm from service department. And you can note down my email ID. Here it is a bottom written, and you can ask any questions through mail ID. And I'll start my session.
Maleshwar, you can put in the slideshow.
Yes, yes, sir. Is it clear?
Yes, sir.
Yes, yes.
Yeah, most of the theoretical part covered by Mr. Girijan, and I'm just covering the topics of software functions and features of the thermal analysis from Shimadzu Corporation. Mainly the thermal instruments from the Shimadzu Corporation is DSC, DTG, TMA instruments. These instruments operated in with the TA60WS and 50 series of instruments, DSC, DTG and TMA instruments. And all the instruments, 4 instruments can be connected at a time and simultaneously can be operated. That means DSC, TGA, DTG, TMA instruments can be operated at one time, and all the analysis can be simultaneously, you can see on screen.
Sir, Maleshwar sir, just a question, go back.
Yes.
There are two things, DSC 60 and DSC 60A.
Yeah.
What is this two?
Yes, ma'am. DSC 60 is the differential scanning colorimeter model 60, and A is the auto sampler.
So, okay, it's an upgradation, same thing.
Not upgradation, ma'am. Actually, if you require analysis, number of samples analysis is more, then manual interruption is more. Instead of that, you can prepare at a time 24 samples and insert in a auto sampler position. Automatically, DSC instrument auto sampler will take care, and you will get all the 24 samples analysis at a time. Means after completion of analysis.
Okay, it means the same information we can get from 60 and 60A. Only difference is the auto sampler, right?
With auto sampler.
Okay.
In DSC 60 instrument, you can analyze at a time only one analysis, means one sample.
Okay.
But in DSC 60 instrument, you can prepare all the 24 samples at a time and insert into auto sampler. And while programming, instrument will take care samples one after another. After completion of first sample analysis, automatically auto sampler will take care for second sample, and the data will be saved in the database. Means whatever the file base we are saving in the path, it will take care, and it will continue 24 samples analysis. Say example, each sample, if you are running 10 degrees centigrade up to 600 degrees centigrade, say example, and each sample will take approximately 1 hour time. If you prepare the entire samples in the evening and you run the sample analysis and batch run, and DSC will take care entire night analysis and completes all the 24 analysis samples. That is the advantage with the auto sampler. Is it clear, ma'am?
Yes, yes, yes.
Continuing to next slide. Mr. Girijan has explained different options is available in DSC 60 models. And with respect to temperatures, from below ambient temperature from -150 degrees centigrade to up to 600 degrees centigrade, this instrument can be used. From -150 degrees to 600 degrees centigrade, that means below ambient, we have to use the cryogenic applications like liquid nitrogen or the chillers to be used along with the instrument. And from ambient to maximum 600 degrees centigrade, the instrument will take care with its own heater mechanisms. Some of the applications like pharma applications, most of the pharma industries and food industries, the below ambient temperatures are used. That is ambient to below temperatures by using the chillers or liquid nitrogen. And when it uses liquid nitrogen, generally liquid nitrogen goes up to -196 temperature. But with the instrument application, it goes up to -150 degrees centigrade. And some of the electronic and semiconductor industries from below ambient to maximum temperature up to 400 people are using. In Geetham University, also in Vizag location, in semiconductor division of physics, Professor Ramesh Kocharlakota using DSC and TGA instruments from Shimadzu Corporation. When it comes to principle of operation, already Mr. Girijan has explained very clearly. The sample and reference is heated simultaneously. When the sample is melted, the sample melting temperature is reflected as a delta T temperature. That is the reference and sample difference we will get as a sample peak in melting temperature. This was explained by Mr. Girijan, and I'm continuing with this how to integrate the data.
And Malaysia, there was a query from Dr. Lakshmi regarding the thermocouple. I think you are the right person to answer that.
Yeah, thermocouples.
Right.
Yeah, actually, my question is, sir has mentioned in heat flux DSC equipment,
Right.
We can use equipment only single thermocouple can measure the difference between the temperature of reference and sample. How does it possible actually?
Ma'am, in heat flux and power compensation techniques, the heat flux technique is used only single heater.
Okay.
Heating mechanism is a single heater.
Okay.
And thermocouples are two thermocouples. One is the reference thermocouple and second one is the sample thermocouple.
That's right.
And heater is having its own temperature measurement technique. Okay. Say example, when heater is connected to one thermocouple, it is called heater thermocouple. And heater is a single heater.
Okay.
And two thermocouples, one is a reference thermocouple and second one is a sample thermocouple.
Maybe it has two readouts and it will calculate automatically.
Yes. Yeah, when we are measuring heating the temperature, we will get three temperature signals. One is from heater temperature, second is from reference temperature, third is from sample temperature. Okay. When the heater temperature heats, say example, when we are running the temperature program from 100, say up to 100 degrees centigrade with the rate of say 5 degrees centigrade. That heater is increased its heat by using, next time showing the slide, it is a PID controls, proportional, integral and derivative parameters. By using the software, this PID controls, heater is increased with respect to 5 degrees centigrade up to 100 degrees centigrade. And at that time, heater is connected to the thermocouples with a heat sink material. This heat sink is it's a very packed heat sink, and manufacturer is taken care by avoiding all thermal losses. Okay, when the heater is heated, that both the reference and sample temperatures are thermocouples are detected with respect to the heater temperature. Right? When it is in, say example, when the green and blue color identifications are there, say take a green as a reference and a blue as a sample. Assume when the green line, both the heater is heated, both reference thermocouple and sample thermocouple both will heat. Okay. It starts heating and both this line means both are increases at 50 degrees centigrade. At both reference and sample is at 50 degrees centigrade. When it goes up to 100 degrees centigrade, the reference and sample both are in straight line, right? Means it increases. When it comes to change in the temperature of reference and sample, that is a delta T, we are calculating reference, either reference minus sample or sample minus reference. And all the time, from ambient to say 100 degrees centigrade, the reference temperature and sample temperature is approximately same, and difference will come as a baseline. When it is a baseline, if you see here, there is no melting up to this place. Baseline is right because the difference between the reference and sample is almost zero. Okay. When it comes to power compensation technique, there are also two thermocouples are there, detectors, but the difference is two heaters are used. The heaters, both the heaters are heated based on the program applied and the technique used in the mechanism, and the thermocouples are detecting. And the delta T also measured same technique. But because of the two different heaters are used, there the heat rate can be increased very fast. That is one option, and high temperatures is possible.
And one more thing, sir has mentioned in power DSC.
Power compensation, right?
Yeah, power compensation DSC means to nullify the difference between temperature difference between the reference and the sample. The extra power sometimes need to be supplied. How we can calculate that extra power supplied to the system to the heat capacity?
Extra power means it is not externally, it is taken care by the instrument manufacturer's software. The software will compensate, ma'am.
Okay.
Right, because all the time instrument will read the heater temperature of reference and sample and see that it is maintained. That is, the power is maintained between the reference heater and the sample heater, and that software will take care the difference between those two heaters power to be maintained. It is not externally, it is through software.
But at some point there should be some difference to show, right? But means the point
yes,
is
ma'am. Why? Because both the techniques are well-known techniques, and manufacturers also using the well-known, and some are means it's having its own advantages with every technique.
Okay.
When it comes to heat flux, the heater is a common, and reference and sample, both the detectors are heated at same temperature, and the heat loss is less, means the thermal loss is less, and most of the manufacturers are using heat flux. And when it comes to power compensation technique, there is some advantages. Yes, some advantages when the heat rate increment is very fast, and the high temperatures can be go up to high temperatures. And that is the advantage with the power compensation.
And Malleshwar sir,
yes,
actually, if I remember correctly, what is the 5 degrees centigrade heating rate is optimum, right? All the time. We normally use 5 degrees centigrade per minute.
Okay.
What is the lowest rate we can use?
Yes, ma'am. I can explain you in method settings in next slides, actually.
Okay, sure.
No problem, I'll continue. With the Shimadzu instruments, you can start from 0.1 degree centigrade per minute or 0.1 degree centigrade per hour is the rate of increment can be selected.
Oh, that's here.
See, ma'am, there is a 0.1 degree centigrade per minute to 0.1 degree centigrade per hour option is available.
Wow, great.
And maximum temperature is, rate temperature is a 99.9 degrees centigrade per minute to 99 degrees centigrade, 99.9 degrees centigrade per hour is possible.
Okay.
In general, our application is either 5 degrees, 10 degree, exactly. But you can opt minimum of 0.1 degree centigrade per minute or hour, and maximum of 99.9 degrees centigrade per minute oblique hour.
Okay.
That can be possible.
Okay.
Yes, ma'am?
Yes, sir. Please continue, sir.
Yeah, these PID parameters are very important, and these potential integral and derivative parameters. Actually, Shimadzu is having the heater mechanism is a patented mechanism. It's a material is called inconal material. It is a patent and confidential complex material configuration. And by using this material, Shimadzu instruments are controlled through PID, and PID is a predefined manufacturer settings. If, say, example, if you want to increase the rate of change at particular location or temperature location, you can change this PID parameters, and you can customize your PID parameters. But basically, we recommend to use a manufacturer settings, but you can customize the PID parameters. That means a heater rate of change temperatures can vary by using the PID parameters. Already, Girijans have explained the DSC curves, how to means endothermic and exothermic. And some of the manufacturers, they indicates the exothermic in the negative direction. Don't confuse it. They will indicate that manufacturers printout diagram in bottom direction or upper directions. You ensure that while referring any other manufacturer's data, the data, whether it is a exothermic or endothermic, when it comes to Shimadzu, endothermic is in negative direction and exo in the positive direction. But some other manufacturers, they will give exothermic in the negative direction. That means you have to read that data as a exothermic in positive only. Then how to read the data? That is, integrate the data is very important. Most of the times, users are doing mistakes by calculating the integrating parameters. When you get some endothermic peak like this, and how, this is not a melting point of the peak. Peak is not the melting point, ma'am. Actually, peak is we need to calculate by joining the two tangents from baseline to peak starting. If you see in the below figure, the DSA curve begins to depends from its baseline. This is the baseline. And the other point of the B, this is in the same figure, at which the gradient of the ascending or descending part of the peak, the quasi-peak, consists draw the respective tangent line. That means the AC and BB, if you draw the tangent, whatever the quasi point you will get, this is called the melting point, not peak as the melting point. Always we need to mention this as a melting point of this particular sample. Generally, most of our users are considering the peak as the melting point. We need to consider this quasi point of this P is the melting point.
Means where this baseline and the B line intersecting, that is the melting
whatever the
point.
Tangent of A and C slash is the one tangent, and B slash is the second tangent. Where the tangent is meet, the point is P. This is a melting point.
Okay. And also, Maleshwar sir, another question. Is there any property like these peaks sometimes asymmetrical, symmetrical, right? This exo endothermic.
Yes.
Is there something, any chemistry behind this one? Like how some peaks are asymmetrical, how some peaks are symmetrical? What information we can get out of this symmetry? Is there any significance for the symmetry really? Because after showing you showed this is a bit asymmetrical. You were just made it two tangent lines and this crossing.
Sometimes you can see the very broad and almost flat peaks.
Yeah.
In such case, the melting point calculation is very difficult, and that's why we are taking the derivative curve of that particular graph and see that the rate of change where exactly is happening, that we are measuring.
Okay, it means no significance actually regarding the symmetry of the peaks. Understand?
When it comes to the enthalpy also we need to calculate in same way of how we are calculating the melting point. Enthalpy, we are calculating the area of the peak from base to base point. If you see the A is the base and C is the base, the entire area we cannot calculate as an enthalpy, and P to C dash we have to calculate the enthalpy, that is the area under the curve. Area under the baseline we are not calculating, and area under the curve with respect to these tangents calculating, that we are calculating as the delta H is the enthalpy value. The enthalpy we'll get is the joules per gram or joules per milligram values. You
mean the area from P to C, right? Under the area between P and C, right? We have to measure, not A to C.
No, not A to C, P to C hash.
P to C hash. Okay.
Why? Because generally area we are calculating in different calculations. The baseline may be some other location, and we are getting the peak.
But this facility is already
all the manufacturers' software.
Oh, okay, understand. Okay.
That I will show you in next slide how to calculate.
Okay, sure.
Right. Then when it comes to software, say example, two instruments connected under the software, two instruments detected, DSC 60 and TGA 50. Maximum 4 instruments can be connected at a time, and all the 4 instruments can be start and read simultaneously all the 4 instruments data. That can be possible with the Shimadzu instruments. When it comes to front screen of the software, this is a TS60 software communication port. And these are the measuring parameters. When it comes to rate of temperature, you already asked the rate of temperature can be how much minimum we can keep it. The 0.1 degree centigrade, we can keep it as a minimum per minute. And we can change this to hours also, degree centigrade per hour. And maximum can be selected 99.9 degrees centigrade per minute oblique hour. And maximum temperature, we can go up to 600 temperature, as manufacturer's highest temperature is 600 degrees centigrade. And this can be connected, means initial start temperature also. By clicking initial start temperature, we can start, say example, our analysis starts from 100 degrees centigrade, say example. We don't need to start from ambient to 100. Just click this initial start temperature and set start temperature as 100. Instrument will take care from 100 degrees centigrade to 600 degrees centigrade.
Means all the TGA, means all the thermal techniques from Shimadzu only from until 600 degrees?
No, ma'am. It is depends on the model. If it is a DSC 600 degrees centigrade, TGA high temperature the DTG instruments and TG instruments up to 1500 degrees centigrade.
Okay.
Depends on technique.
Technique, okay.
Why? Because I shown earlier this slide. Maximum applications are 450 degrees centigrade. Okay. That's why Shimadzu go up to maximum 600 degrees centigrade. And beyond 600, I feel there is no specific applications.
Yes.
Okay.
Yes.
And there is a connectivity, gases connectivity. Say example, your application is having ambient to 200 degrees centigrade with the nitrogen purging, and after 200 to for 600 degrees centigrade, air purging is required, say example. In such case also, you can automatically select your method by choosing the gases application. If you click gases, first gas is a nitrogen and second gas is a oxygen, say example, air, that can be possible. Software automatically switches from ambient to 200 is the nitrogen purging and 200 to 600 as the air purging. That option is available with software. And like this, you can run 99 programs, say 10 degrees to 10 degrees rate up to 600. And you can, next program is a minus 10 degrees up to 500 degrees centigrade, and minus 20 degrees up to 200 degrees centigrade. Like that, 99 programs can be run at a time. It's like a cyclic analysis. It's clear, ma'am?
Yes, sir.
Right. That means 99 programs can be made, and maximum temperature of 99.9 degrees centigrade you can go. And minimum is a 0.1 degree centigrade. Next is different pans are available with Shimadzu. You can opt aluminum seal, means different. These platinum alumina can be used in the TG high temperatures. More than 600 temperature, we have to use the different materials of crucibles. We cannot use above 600 degrees centigrade aluminum. This will not applicable for DSC. When it comes to TG and DTG instruments, when you are opting for higher temperatures, there you have to use a platinum or alumina, see Al2O3. Different stainless steels are available, quartz available. And when it comes to high temperature and high pressure withstanding, means you have to go with the stainless steel with high pressure type cells you have to use. That options also available.
But the temperature with the stainless steel, until which temperature?
No. That depends on your temperature application, ma'am. You have to go up to 900 degrees centigrade. And if you are using gold.
No. If we are using aluminum and platinum, we can go because they can withstand their high temperature. But stainless steel, what is the withstand temperature with the stainless steel?
At this moment, Girijan san, can you give?
No, I do not have what is the temperature. My temperature idea about the stainless steel temperature. Okay. Maximum temperature I do not know.
Because alumina, platinum,
they can go to very high temperature. Yeah.
Quartz and all high temperatures. But I don't know about
high temperature. Platinum, alumina is
all are actually except stainless steel. I don't know about
stainless steel. I do not know how much is the temperature.
Yeah.
That will clarify you, ma'am.
Yes.
Okay. Apart from this, copper crucibles available, gold crucibles also available. Depends on the application. And next is the atmosphere selection. Different atmospheres, you can select nitrogen, air, helium, argon, hydrogen, and oxygens. These options are available with the software. These are the measuring parameters. The measuring parameters are very important because if your measuring parameters are not correct, then you cannot run the analysis also sometimes. If any measuring parameters are wrong, then instrument will not take for measurement. And very important parameter is the rate of the temperature selection. When Girijan-san explained the resolution parameters, if you are running with high temperature and high rate, say 50 degrees per minute, if you are selecting the rate, and you may lose some important peaks like a shoulder hump peaks, and small resolved peaks also you may lose. In such case, you have to run with a very low temperature rates so that you will get a maximum, means the resolved peaks you can increase. That can be, means the instrument will detect all the peaks of your sample. That is a very important parameter while selection the parameter selection. If the wrong selection of the method will not give proper results. When you start the analysis, the window color will change and you'll get some data. Say this is the indium data. Indium is having around 156 degrees centigrade peak, and that can be integrated as the onset 155.4 degrees centigrade and heat of around minus 27 joules per gram. This integration parameters software is available, software provision is available to calculate. If you take a printout with your customized report generation, you'll get a Geetham University thermal analysis with all the method parameters, temperature program, who has done, and what time analysis was done, all the information, you will get it, ma'am.
Okay.
And different software options are available. And for DSC, the specific heat, purity, DSC kinetics options are available, and partial area calculations also possible. When it comes to TGA instruments and DTG instruments, kinetics and partial area is possible. When it comes to mechanical analyzers, dynamic heat rate and partial analysis is possible. Stress strain programs is possible. These all are the optional softwares. In general, all the manufacturers, by default, these softwares will not come as a standard. You have to choose based on your applications. When it comes to specific heat capacity, the specific heat is calculated between the two constant temperatures. Say example, our program, say, different sample analysis, say first constant temperature to rise of the temperature, and again it is maintained. In between the constant temperatures, we can calculate the specific heat for different samples. That is, you'll get it from specific heat. This is one of the example for SBR sample. The specific heat is calculated at different points, different temperatures. And second application is the purity. It's the Van Hoff law. Based on the Van Hoff law, the purity calculated as per this formula. And purity, we will get it as a purity percentage in the result when we calculate the sample. When we calculate the sample at start and end and at particular 238 temperature, the purity of the sample result will give it as a percentage. And same information we can calculate onset, offset, and heat enthalpy with the different units we can calculate. When it comes to kinetics, with a different rate of temperatures, we have to analyze the samples, and we can calculate by using the kinetics software. And kinetics will give the kinetics results. These are the calculations we will get it from software. When it comes to different options, instrument is having options like derivative parameters. First derivative, second derivative can be possible by using this software. And other options also available like a smoothing, baseline correction. Sometimes baseline correction is required with respect to the blank. That can be possible. And heat corrections also required. And the user has to correct some baseline and heat corrections. And derivative corrections, derivative is possible.
Means, Maleshwar sir, this is a derivative means, again it comes as a DTA, you mean derivative means that one?
Yeah, derivative of TGA is possible, derivative of the
No,
DTA is possible. This is a
a
derivative of DTM.
DSC, right? This one?
That is a DTA curve.
DTA curve.
Yeah, DTA. That DTA, you'll get it a microvolts direct signal is converted and calculated like earlier Mr. Girijan explained how the delta Q is calculated with respect to the temperature. Delta T divided by R is calculated as a delta Q. It is in milliwatt and same value. And whatever the derivative of the graph, it is looks like a pink color. Generally, when the normal peak is derivated with respect to, say, example, here the temperature is the reference value. D milliwatt divided by dt, we will get as the derivative peak of this particular curve. When there is a broad peaks you are getting in the analysis, you cannot see the melting point and other peaks you cannot see.
Yeah.
When you derivate the data, if you see the zero value, this is the zero value. This is the peak of this particular curve. When it is in a flat, broad peaks, when you are getting with the normal calculations, you will not get any peak and melting points. In such case, you have to find out where exactly the peak for that broad flat peaks. Derivative it, you'll find this such a beautiful option, derivative option is available. You can find a derivative of particular peak of this peak when it is in a broad or flat. Okay.
It means that we are thinking one peak is there, but in real scenario, there are two peaks are there, right?
No. When it is in a derivative, actually derivative say this is the peak, ma'am, red color one.
Yeah, that is the peak.
When it is in a red colored one, when you derivate, the rate of change from this point to this maximum position is increasing.
Yeah.
When it is an increasing, one certain place, the rate of change is not there. If you see the mid place, the rate of change is very less.
Okay.
And when it is in a very less, the rate of change will come down to zero. When the maximum position, the rate of change is almost zero. And that is a zero. When the rate of change is, again, it is increasing position, that this increasing position will increase. And from this place to again base position, the rate of change is very less.
Okay.
This curve will indicate this one.
Okay.
That is for one peak. if you derivate, you will get a one positive and one negative. Because the rate of change is increasing, and at what particular position there is a 0 for rate of change. That 0 indicates this position. There we are calculating that as the maximum or peak. If it is a peak, such a graph is there, then the calculation is difficult. When it is in a broad and flat peaks you are getting, that time derivative is one of the important technique to identify the peaks.
Understood.
Next, these options are available, derivatives and multiple data also you can open from the software. Means two data at a time we can open and analyze. That option also possible in softwares. For comparison studies, if you want to see both the peaks where exactly it is a matching, two data can be opened and calculate. That options are available. When it comes to below ambient temperature applications, you have to connect either liquid nitrogen or electrically temperature chillers. If it is a manual liquid nitrogen filling, there is an option in the instrument itself. Directly you can pour liquid nitrogen in the instrument. The furnace is directly connected to the liquid nitrogen chamber. When it's in with ambient to normal high temperatures, the heater is taking care with respect to the program. And this is a reference and sample and heated in the single heater and measured with the two different thermocouples, and we are getting the data. When it is in poured liquid nitrogen for below ambient temperature cryogenic applications, this, liquid nitrogen is at minus 196 temperature, and this chamber is cooled by the common heat sink material. And when the low temperature is maintained, and this heater also is in controlled heating position only. Whatever that based on our method and program, the temperature is controlled, and when it is in even minus 196 temperature, heater is maintained its own temperature. If our temperature rate is started from minus 150 to 200 as our parameters, the software is taking care by heater and these temperatures, these thermocouples, and software starts the heating temperature from minus 50 to say 200 degrees centigrade. That can be controlled. That options are available in the instrument that can be controlled through software. If you don't want to mechanically fill the liquid nitrogen in instrument, there is options already explained by Girijan sir. There is a temperature controlled chillers are available. This chiller can be connected to the DSC instrument. And automatic can be connected directly to the instrument. These options are also available. And still DSC, then I can clarify, ma'am. Any team members?
No, sir. It looks very small, but a very powerful equipment.
When it comes to TGA instruments, that the thermogravimetric analysis, Shimadzu is having two different models. One is the TGA 50 series and 60 series. This is a TGA 50 series where in Vizag, Geetham University is using same model. The balance mechanism is a suspension type balance mechanism. Here the balance is only sample side mechanism only heated and reference is in ambient temperature. That's why from TGA 50 series instruments, we will get only the TGA curve, not DTA curve, because DTA require reference side also to be maintained in the same temperature. That is not possible in this suspension type. It is having like a fulcrum is there. That fulcrum reference side is in ambient and sample side only it is in furnace. That's why we'll get a TGA curve and we will not get a DTA from TGA 50 series instruments. This is the mechanism, and sample is in outside the furnace, and reference is outside the furnace and sample is in the furnace. The mechanism is a fulcrum based one, and whatever the sample and the reference weight, it is a compensated and read as a baseline initially. When we keep the sample as the sample and heated with the furnace temperature, we will get a TGA outcome. And second model is a differential thermogravimetric analyzer DSC60 model. The first one is the without autosampler, and second one is this is the with autosampler. And Shimaju also having a high temperature models like a DSC60 with H and DSC60A. A indicates autosampler with high temperature is available. And normal model goes up to 1100 degrees centigrade and high temperature goes up to 1500 degrees centigrade. This is the top loading type mechanism, and at a time we can keep a sample and reference in the same furnace. By using the sample and furnace adjacent, and we will get a, simultaneously we will get the reading of the sample and reference, and we are heating sample and reference simultaneously. We will get a DTA curve here. The sample reference pans are located at the end of the balance beam. This minimizes the heat transfer from the furnace section to the balance unit. There is a below balance unit is there, and that heat section furnace is there. That minimizes easier sampling handling. This is the mechanism of the DTG60. The below is the balance. Here balance is very sophisticated balance used by Shimaju and furnace, and here the sampling section. The mechanism used is the Roberval mechanism. Yeah, this platinum alloy band is almost thinner than the hair, ma'am. It looks like a less thickness than the hair. It is very sensitive, and this compensates the weight of this balance. This mechanism, Roberval mechanism.
With like this nano wire.
Sorry.
Then it is a nano kind of thing.
Yeah, very less than hair. Less than the thickness of the hair.
Yeah, maybe it is a below nanometer. The hair is about nanometer. Yeah.
Right. And this such a balance, critical balance. We are even if any happens, means user level any mistake happens and broken, we are repairing these balances. We have a very sophisticated engineers and trained engineers, and we are repairing this balance at user level itself. No need to send any factory. Only Shimaju can do such a sophisticated repairs at user level places. And this mechanism looks like this, and these all are platinum alloy bands. And this whatever I have said, it is almost less thicker than the hair. Such bands are available, and at the time of installation and at the time of repair also very taken care by engineer, and they will see that the mechanism is maintained, and you can go up to 1 microgram level of balance, means change you can measure with this balance. When it comes to DTG, DTA detectors, the side-by-side detectors you can see like this, reference and sample. These two are plug-in type. You can remove and insert the detectors. When it comes to auto sampler, the 24 samples at a time, you can keep it in instrument, and overnight analysis possible. Say example, ambient to 1000 degrees with 10 degrees rate increase, you are using your sample analysis. That means approximately 90 minutes, say 30 degrees is the ambient, and 1000 degrees your analysis time. 1000 minus 30, it is a 970 temperature of 10 degrees heat, 97 minutes it will take each analysis. And cooling, it will take another 30 minutes. That means for 10 samples analysis, you require almost a 15 hours time. If you prepare all the 10 samples at a time and keep it in auto sampler, overnight analysis is going to complete, and you'll get a next day morning your entire sample analysis in handy. That is possible with the auto sampler type of instruments. 24 samples tray and allows continuous analysis, built-in compact auto samplers. The tweezer to carry samples is equipped with a pinhole mechanism. Whatever the tweezer used in the equipment, it's a very sophisticated arm mechanism used in the instrument. Here again, when it comes to DTG, TGA instruments, parameter setting is a very important. If you are missing any parameter, then you lose your sample data. Sample parameters are very important selections. When it comes to DTG, the baseline is almost a 0 microgram level of baseline. You will get it from DTG 60. When the data comes, data can be calculated by using the software. The weight loss can be calculated from the starting point to ending point, or wherever the weight loss is calculated, that can be calculated from this particular temperature to temperature. This is one of the samples weight loss is calculated. This percentage of weight also can be calculated, or milligrams of weight also calculated by changing the scale of this y-axis, TGA axis. And this is the derivative. When we did it for TGA curve, the derivative curve, what we got it for these two weight losses. These options available in software. Derivative curve of this is the left side one is the TGA percentage, and the right side one is a derivative TGA. The derivative curve of the molybdenum oxide, one of the sample TGA curve with respect derivative curve of this molybdenum oxide. Approximately at 642 degrees centigrade, molybdenum oxide is having the weight loss approximately 10.8%. And when it comes to PET, it's with respect to air as atmosphere. The weight loss can be calculated, and from weight loss, almost weight is lost approximately at 800 degrees centigrade. When Mr. Girijan was explained the calcium oxalate monohydrate, the calcium oxalate monohydrate can be taken as the reference material for TG instruments. DTG instruments, and DTG we will get a calcium oxalate monohydrate if you run up to temperature of 1000 degrees centigrade. The 1000 degrees centigrade value, all the three compounds, like a first temperature at water will lose. This is a bonded water, and after that CO, carbon monoxide, and CO2 will lose. These are approximately first water molecule divided by total calcium oxalate monohydrate. That bonding water will lose at 12.32% at somewhere at below 200, and after that CO will lose and CO2 will lose its weight. Based on this, we are calibrating the DTG instruments to get the accurate readings. That is a DTA. And for temperature calibration, we are doing with the indium and tin materials. Indium and tin is having very pure metals of 99.999 pure indium. We are calculating at 156.7 degrees centigrade. With that, we are, if required, any corrections are required, that can be possible in software. We are doing corrections. And when it comes to the data can be ASCII option is available in software. You can convert this to ASCII, and you can plot your own techniques by using Excel or some other softwares. And this ASCII option is available.
Sir, Maleshwar sir, can you go back to previous slide?
Sorry?
Can you go back to previous slide, previous one? Yes, this one here. If you see that the before one. Just now you showed no.
This
one?
No. The previous slide. Yeah.
Yeah, this one. This one, yes.
No.
This one.
Yeah.
No, that one, this one only, yes. This one here, if you calculate the percentage weight loss, that is 12.57, and which corresponds to 0.8573 milligrams weight. How we can determine this? This is from water only, because the water is 18% CO. If you take 28%, this is how we can say that this is
Right, ma'am.
this weight
Say
loss is from CO, this weight loss is from water and CO2 based on the percentage
right.
weight loss.
Right. The calcium oxalate monohydrate CaC2O4H2O is the compound, and from this, this is a known compound. And when you are rate of increase, if you are increasing with 5 degrees centigrade per minute, you will get a TG curve of this one, green colored one.
Yeah.
Okay. When we got this data from that TG instrument, when you are calculating the TG from, say, ambient to 200 degrees centigrade, if you are calculating weight loss, if the weight loss comes as a 12.57 example, and this 0.8753 milligrams of the total weight loss happens from the actual weight taken. Say, example, if you take 10 milligrams of sample, out of that, this is the weight loss. That means 12.57% loss. If you calculate 10.57, say example, water molecule H2O divided by CaC2O4H2O molecular weight, you will get a 12.32, you will get it, ma'am.
Oh, like that. Okay. Understood.
Whatever the water molecule we are losing here, weight loss, that water molecule divided by the total molecule weight of the calcium oxalate monohydrate, the theoretical value is the 12.32. Whatever I have got it from the software calculation is it's 12.57. Theoretical value is 12.32.
Understood, sir. Understood.
And when it comes to second peak, this is a second loss. This is a CO divided by calcium oxalate monohydrate.
Okay.
Loss. If you calculate manually CO molecular weight divided by calcium oxalate monohydrate, you will get approximately 19%. And when it comes to third step, CO2 divided by calcium oxalate monohydrate, approximately 30% of weight is going to lose here.
Okay.
And when we are installing or verifying the instruments, we are verifying these entire data. And if any variation in the percentage loss, that means either mechanically adjustment or software adjustment, we are doing at customer places, ma'am.
Okay.
This is a mandatory because instruments are transporting from various locations. Say, example, if it is a Shimadzu, Japan is transporting and reaching up to, say, Bangalore. And so many mechanical variations are there. Those things we have to compensate. For that, we need to calibrate the instrument. If required, adjustment is required. Those things we are doing with the known standards. Say for TG analysis, TG graph, we are doing with the weight standards and calcium oxalate monohydrate. This is the well-known acceptable parameter in industry. When it comes to temperature, we are doing with the known standards like indium, zinc, such standards.
Understood, sir.
Clear, ma'am?
Yeah, yes, sir. Very clear.
Yeah, this data can be converted in ASCII value. If you want to convert this to Excel or any other your own mechanism of drawing the graphs, you can convert it. This option is available. And when it comes to selection of cups, different cups are available. And I'll clarify you the stainless steel temperature. Remaining is aluminum can go up to 600 temperature. Platinum is up to 1000 generally we are using. And alumina can be go to up to 1600 temperature we are using. And this is a normal crimping, and hermetic means liquid samples also possible. With the here it is a 9 is there. This is a high pressure withstanding pressure proof cells. And these are, if say example, if your sample is having pressure withstanding samples, means that this such type of crucibles to be used.
Okay.
Clear? Clear?
Yes, sir. Yes, yes.
But TGA also is having a different cups are available. Quartz, platinum, alumina, such cups are available for TGA. And when it comes to your samples, the nature of sample is either powder or granules or film-like samples, fibrous samples, and volatile samples and other types of samples. You need to select your proper crucible for sample analysis. If your sample analysis, say example, yours is some liquid sample and you cannot use like normal cups. You have to choose different cups for this analysis. This is very important for choosing or selection the crucibles.
Okay.
This is my presentation, ma'am. If you have any questions, you can please.
Very clear presentation, sir. Like Girijan, sir.
Thank you very much. Thank you.
So participants, would you like to ask any questions? Some of them actually have posted their questions in the Q&A session and some raised their hands. So I would allow them.
You can read it out, Dr. Lishmi.
Yes.
Yeah. So whoever raised their hands, Jyoti, would you like to speak? And Dr. Reshmi Pundur from Haryana. Would you like to speak? Because I can see you people raised your hands. It seems they are not responding. Then I have a couple of questions in the Q&A, sir. I will take one by one.
Yeah.
So first is Sannapaneni Janardhan. He is asking, is the phase change shown by a polymer at glass transition temperature will represent its stability?
Glass transition temperature is not showing the stability. It is only showing the temperature at which the material is getting converted to a different form. From glass and brittle form, it is getting converted to rubbery and viscous form. It is a change of phase. It has nothing to do with the stability. It is a change of form. And for different types of polymers, the TG temperature also can be different.
Okay. And another person, Siddheswaran, can you say the use of thermal analysis for grown crystals? What kind of properties can we use thermal analysis for grown crystals? What kind of properties are analyzed? Can be analyzed, it seems.
What crystals it is?
He has some grown crystals. He is asking whether thermal analysis can be used for grown crystals. If so, what kind of properties can be analyzed?
What exactly is looking for in these crystals? So that is more important.
Crystallization temperature, you can use it.
Yeah, if it is a crystalline material,
yes.
And during the course of thermal analysis, if it undergoes certain transitions like melting or crystallization or even decomposition, all those transitions can be studied by thermal analysis.
Yes, yes. And one more question from him again. Is it possible to analyze the qualitative decomposition precisely using thermal studies?
Malleshwar, I think if you have the partial area software,
is available.
Partial area software is available. In that case, it can for quantitative analysis. But without that, it is not possible.
Okay. And one more question from Dashinde. Can TCA graph use information of melting point of sample? TCA graph, can we get melting point temperature using TCA graph?
TCA graph, no. TCA is only for weight loss. TCA graph will give you only information about change in the mass, weight loss or weight gain. But if you want to know what is the melting temperature, either you have to go for a DTA or a DSC system.
And one more question. Arjunan, I have any one graph, TGA, DTA, DSC in my hand. How to easily identify the DGA graph or DTA graph or a DSC graph?
DSC graph and DTA graph will look alike. There is no problem. There is absolutely no change. If you look at the DSC graph and the DTA graph, they are going to look almost same. There is absolutely no change. Okay. You can differentiate DT and DSC from the data that you are going to get. Okay. Whereas a TG can be very easily differentiated because wherever there is a change in the weight, change in the mass, there is going to be a spike in the baseline. So that, correct now, Maleshwar, you want to add anything?
Exactly, sir. The question may be by seeing the three graphs, how to identify which one is the TG, DTA, or DSC.
Correct.
DTA and DTA, there is no much difference because the units are only the difference.
Yeah.
And the sensitivity is the difference. When it comes to TGA, loss of the signal will be there. Means the weight loss will be there. It is almost like a straight line, and the loss weight will be there. By seeing the graph, we can identify which one is the TGA or DA. The DSC and DTA is only the difference is sensitivity.
Yeah, but graph shape will be almost same. Will be same.
So Virendra is a PhD scholar. He is asking one more question from the same person, Dashinde. What is the best rate means temperature per minute for characterizations of samples? That's what Sir has mentioned already, 0.1 degrees centigrade per minute also, 0.1 degrees centigrade per hour also he mentioned.
But that one has to optimize it. By sometimes you have to carry out some trial and error, and we have to come to a optimization of whatever heating becomes. That is our basically your development work. You need to optimize the temperature for your sample.
And the question from Birendra, what is plateau in TGA?
What is?
Plateau in TGA. Plateau.
Plateau in TGA. If it is a plateau in TGA, that means there is no weight loss. Correct, Maleshwar?
Yeah, if there is no weight loss, then there is a plateau.
There is a plateau. There is no weight loss.
And the same question from Birendra.
The same way, whenever the sample undergoes a glass transition, your TG curve is just a plateau. It's just a baseline. There is no step. That means there is no weight. There is no weight loss.
Yeah, and the same person asking one more question. Is it possible to get weight gain during TGA analysis? Yes, of course.
Weight gain.
Yeah.
Weight gain is very much possible.
Very much possible.
Suppose if the sample undergoes oxidation, there is oxygen is getting added. For example, iron, and just take an example of iron. Iron, when it is getting oxidized, it is getting converted to iron oxide. So there is going to be a weight gain. So oxidation, there is always a weight gain in the TG.
So
and the shape of the TG curve is also going to be different. Wherever there is a weight reduction, I told you the shift will be in the downward direction. Whenever there is a weight gain, the shift will be in the upward direction.
So one participant commented, Selva Kumar, yes, excellent clarifications, sir. So that's it from Q&A session, sir, today. And Maleshwar, sir, it's a really fantastic explanation.
Thank you very much.
So far only.
Thank you.
Girjans are only dominating.
That's why I specifically wanted Maleshwar to be here, because Maleshwar, I know he's an expert on thermal. That's why
he is almost there, sir. Maleshwar, sir, almost there, competing with you in the explanations. So thank you so much. That was very in detailed, explanation, and thank you for clarifying my doubts also, because I don't know how to properly use this technique. I will always normally use this one. I am working on nanomaterials. I always use this technique for the stability purpose.
You have a thermal system in your college? You have a thermal system?
No, sir.
Not yet.
No, sir.
Not yet.
No, sir.
Vizag is having.
Vizag is having.
We are planning to buy actually.
Okay.
So very soon we will approach you.
Yeah.
So participants, that's all for now. And we will be joining tomorrow. It would be great if you join early, 9:45 a.m. sharply. And Sir is going to stop at 12:30. And 12:30 to 1 o'clock, we will be having closing remarks. event thing, and our dean and our principal will also join for the closing remarks session. So, sir,
Malaysia, I think I request at least by tomorrow 12:30, if you can log in, you can be a part of the winding up program.
Definitely, sir. Right.
12:30 to 1 is only the winding up program. I request you to be present.
Sir, actually, Girijan sir,
yes.
12:30, if you stop now, we have to take a Q&A and we have to take the feedback from the...
I will stop before 12:30.
Yeah, by 12:10 or 12:15, you can start.
Yeah.
So we will take a Q&A.
Achha, in that case, Dr. Lakshmi, I just want to ask you very frankly, tomorrow, whether for GC, whether you need that software part, because that will unnecessarily prolong.
No,
software
sir,
part is not required tomorrow.
No, not required.
I'll ask that boy to be present because he was there with us for 2 days. But I don't think that software part is required. Unnecessarily, it will get delayed. Let him be present. If there is any question answer, if he can answer some question, no problem. So I'll ask Mr. Amol to be present, but we will not take up any software part tomorrow.
No, not required, sir.
I think that is not required. Okay, so that by 12:15 I can.
Because mostly whatever they are covering, you are covering already in our thing. Only just showing the how to use that software application what they are showing.
Yeah.
So I don't think it is required. Tomorrow we will skip that part so that we can
software part will skip.
Yeah, we can save some time. Okay, so
tomorrow from 12:35 to 12:15, if I stop, participants have the freedom to ask any questions related to UV, FTR, thermal, or GC.
Yes.
Malaysia also will be there, and Amol also will be there. And anything related to, he is also, Malaysia Rao is also an expert on the UV and FTR, madam. He is an expert, the expert on UV and FTR. So if there is any query related to UV and FTR, anything related to hardware, system, software, Malaysia Rao will be there tomorrow.
Okay.
Last part, I mean, after 12:15, he will log in. So he can also be present because he's a very important person.
And we can take Q&A also. As you said. And definitely we need to take feedback from the participants.
Yes.
It is online. On live, we will request them to, if anybody interested. So after that, our dean and principals will be joining at 12:30. So once they join, then we can do the closing of the program.
By 1 we can finish.
Okay,
so
sir.
Malaysia be there tomorrow. But after 12:15, you can log in. And there will be about 15 minutes question answer from 12:15 to 12:30. So you can be a part of that.
Definitely.
Yeah, thank you, Malaysia.
Thank you, sir. It's my pleasure to listen to you. So all the participants have been posting here links and links for feedback and attendance. Please fill them. It is compulsory to get e-certificate. Okay, thank you for your active participation throughout the session.
We will start sharp at 10 o'clock. We will not wait for a minute more. We will start at 10 o'clock sharp.
We should. I think I appreciate all the participants if you can join tomorrow by 9:45 a.m. And looking forward to see you. And sir, looking forward to listen to you guys both tomorrow.
Thank you, madam.
See you, sir. I will be closing this one then.
Okay.
Thank you very much.
Okay, thank you, Malaysia. Thank you. We will log out.
And also participants, we will be, if anybody interested to have YouTube links separately email to us, then we can send
and we'll
them
be sharing our contact details also. Malaysia, myself will be giving our email ID as well as mobile number. Anybody wants to contact us later also, you are welcome.
Tomorrow you put up a slide, sir.
I have a slide for my email ID and
Yes. If anybody wants, then definitely they want. Okay, sir. See you tomorrow.
Thank you so much. Thank you. We are logging out.
Yes, sir.
Okay, Malaysia. See you tomorrow. See you tomorrow.
Participants, I have posted several times feedback and attendance link. Please fill them if you want e-certificate. Please scroll up. Several times we have posted. Okay, I'm sharing one more last time. After that, within 2 minutes, I will be ending the meeting. This is feedback link. Sir, the day one feedback link not able. Yeah, we closed it, sir. Actually, so, tomorrow, sir, if you want to give the feedback online, please, I will welcome you to do so. Sir, you scroll up in the feedback I posted, sir, already. Sir, I appreciate if any one of you, I am going to ask you to give feedback online tomorrow. I really appreciate if you can talk about the workshop, this 4-day workshop tomorrow. That would be great. It would be encouraging for us to arrange more like this if we can give feedback, whatever the good or bad or whatever. So Kanan sir, please scroll the chat box up. You can find the feedback and attendance links several times we posted, sir. See, don't worry. We have an option in Zoom. Those who attending, we are getting attendance from the Zoom. So definitely, if anyone misses to fill the attendance form, also they will be getting the certificate, because we will be getting the details of the participants who attended the session from Zoom automatically. In Zoom, there is a provision called it will take the attendance of all the participants. That's how, since we are subscribed for this. Thank you, Sridevi ma'am, asking one more time. I'm posting here the attendance link. This is the attendance link, madam. I think it is going to, okay, now I understood. See, this is the attendance link. That is feedback link, I think. This is attendance link. I'm closing. Thank you so much for your active participation. Please join early tomorrow by 9:45 a.m. And if you have any questions regarding all the techniques that are covered in this workshop, like UV visible spectroscopy, FTIR spectroscopy, thermal analysis, today's topic, and tomorrow sir is going to talk about chromatography. So on all these topics, if we have any doubts, all the people that are addressed, who are addressing these topics will be there tomorrow. Then you can ask questions. Thank you so much, and I'm closing my window.